Can you hear me? OK. Yeah, welcome everybody to the CSM tutorial. Then we are very excited to have you here. And it's going to be a very packed week, but we really hope that you will learn a lot and that you will become part of the CSM community. Yeah, then this is the Mesa Lab. It's a beautiful building that I recommend that you explore a little bit around the exhibit also when you have a chance. Before starting, we want to do a land acknowledgement. Then the place where the Mesa Lab is constructed is located on traditional territory of the Cheyenne, Arapaho, and Ute, and many other Native Americans. And also something very important to us, this is the code of conduct. And then by being part of this tutorial, it means that you are agreeing to respect all the value that we have here, then share the air, then don't be the only one talking in the room, show appreciation and acknowledge teamwork, listen to understand, communicate context, value new idea and encourage innovation and offer constructive feedback. Then we expect you to respect all this value. There is our vision here from, sorry. Okay, oops. Oh my gosh. Okay, then I don't know how to use this thing. There is our vision, the CGD vision for the code of conduct, and we have also a DEI office, the UCAR DEI office, and you have more information on this website. Then the primary point of contact for this tutorial, this is me, and this is Elizabeth over here. You got many emails of her. This is that you can put a face, but it's not like a two-people effort. There are plenty of people that have helped for this, and you will meet them through the week. Everybody will have a badge. The helper will have also, and the speaker will have a badge. Please keep your badge all week. Sometimes people wear it on the first day, and then the badge disappears. Try to have your badge every day. Then it's easier to identify. Then this is the goal of the tutorial. We want you, at the end of this tutorial, to have an understanding of CSM, the core component, and the feature, that you are able to run the model and modify and use the output. You will have also opportunity to network with your peer and other scientists of CSM. Also, you will have an understanding of the supercomputer at NCAR. And also, we want you to perceive the tutorial to be a very inclusive environment. How we are going to achieve this? Then you will be there all the time this week. Then this is the website of the CSM tutorial. If you have forgotten the link, you just Google CSM tutorial. It will bring you right away. Oops, sorry. Then it will bring you there right away. And then you will see here you have the agenda. And then you have the lab material that's over here. Then this is really the two important links, but there will be also a photo gallery. We'll take picture over the week. Then there will be also a photo gallery going there. Then the agenda will be like this. You will have lecture that will be happening here in the seminar room. We will have lecture on every model component, the atmosphere, the ocean, the land, the sea ice. But we will have also some lectures that are on other topics, climate variability, variable resolution, and all the day you will have lecture. And then we will have lab activity. Day 1 to 3, you are going to really learn the basic, how to run the model. Everybody will do the same exercise. And then on day 4 and on day 5, we will start to split. You will have the challenge exercise for every component of the model, and you will pick the one you want, and you can also pick 2 if you want. And on the last day, we will do some plotting and diagnostic of the output. This is for the lunch activity. Then the lunch will be in the cafeteria. They will be mapped at the end of the presentation. You will have food over there. Then during lunch on Tuesday, Wednesday, and Thursday, you will be able to meet an NCAR scientist and have lunch with the person. It will be a casual conversation with the scientist. To have this, we ask you to fill a form. A lot of you have already filled a form, but if you have not, the deadline was yesterday, but it's not too late. We will do the assignment today. We will assign you to one scientist, and I have looked at the list. There are a lot of scientists that everybody wants. Then you will be assigned to one. It's maybe not your first choice, not your second choice. It can be your third choice, but there is no better choice. And it's really to learn a little bit about these people. Then if you haven't signed up, I invite you to sign up for this. And the last thing, there is like the Mesa Lab exhibit you have seen in the hall, then we encourage you to see this. If you want to be part of the public tour, there is a public tour Monday, Wednesday, Friday at noon. Then you are welcome to join this, but it will not be only for the student or the people over here. It can be sometimes busy, but you can just explore the exhibit on your own. And this is a typical day. In the morning, you will have lecture, and then here in this room, and then we will have lab. We will move to the library that's on the top floor over there. And then after you will have lunch, you can participate to meet scientists activity. And then we will come back in the afternoon, and again, we will have lecture, we will have lab, and we will have a daily check-in. And I don't know, did I yet add stuff this morning to the slide, but okay. Yeah, then snack, I yet add, but don't show the last version of the slide. Okay, there will be snack in the morning. The snack will be just here in front of the seminar room. We ask you to move fairly quickly through the snack because we have a very packed agenda, but then you cannot bring back food inside this room. Then be careful about this. Then you eat your snack there. Then in the afternoon, we will have snack in the diamond room. You will see the map at the end. Then we will be in the library, but you will have the snack in the room next door. Then this is the snack situation. If you don't know, you ask me or Elizabeth where the snack are. Then also something that we will have every day, we will have a daily checking at the end of the day. Then after, it was on the slide here, at the end of the day, we come back, after the exercise, we come back here for 15 minutes. Then there will be a daily checking where we discuss what went well and what didn't work that well. But also we will ask you to fill a daily survey about the lecture you had during the day. And it's really to see how the lecture was relevant to your interest and need, and if they were the right level, and also if you have any feedback. Be constructive feedback when you do this. If you write, this is not like rate my professor. It's something nicer than this. But we want this to be useful for you and for the next people. Then it's why we're asking you this. And on the last day, there will be also a general survey. But it's important for us, then please fill this. Also, there is no question that's stupid. If you have any question, don't agonize on your own, ask questions. There will be many helpers. Then really it's important. You can ask your neighbor, you can ask me, you can ask Elizabeth, you can ask anybody. And don't be ashamed, you are not supposed to know everything. Then the wireless access. Then you are going to do the exercise, and if you want to check the email, you will have to do the wireless access. Then it's the UCAR visitor, and it will ask you to do a registration to access it. You have also the EUDRAM wireless that might be installed on your computer, then you can use it. And very important also, for the tutorial, you have a special account to run on the supercomputer, and we have also a reservation queue. It means that it will give you a priority of everybody in the country who wants to run on the same computer. Then all the instructions are on the lab material you look for tutorial one-time setup and tutorial queue and account. We will come back to this many, many times, but it's important that you set it this way. Otherwise, you are going to wait in the queue for a very long time. And if you have any problem, if you don't know, if you forgot what I say, you called me or anybody. Also, we create a GroupMe channel. It's to allow you to communicate with each other. Then I saw a lot of you have already registered over there. Then I didn't want to post the link here because it's going to go online, and I want that this is only this group that have access to this channel. Elizabeth sent the link, but if you don't have the link anymore, ask us. We will give it to you. Also, on Thursday, there will be a special CGD cafe where you will be able to meet more scientists and admin and staff from the Mesa Lab. Then it will be a fun event. This is map. Then this is, I got this from last year, but there is the cafeteria. We're in the seminar room. We will eat at the cafeteria. Then there is like the tree plaza here if you want to relax at some point. There is women's restroom here when you walk towards the cafeteria, and there is also the men's restroom over here, just behind the security at the entrance. And upstairs there is like an all-gender bathroom. And bathroom you need to look a little bit, but they are here. This is the map for the next floor. This is the library where we will do the exercise, and the diamond room where we will have the snack in the afternoon, and also you are welcome to move there if you find the library is too packed for you. And also we have a few quiet space. You can ask our admin team, then there are quiet room, you can do some outdoor sitting, or there are several walking that you can do around, and this is, yeah, you're welcome if you need space. Then if you have any question, ask us. And then, yeah, I see people, it's my son who is probably about your age that did view of Minecraft of the Mesa Lab. If you have any question, ask us. We are going to have the first talk. Any quick question now? We have 1 minute. Otherwise, I will invite our chief scientist. Yeah, that I didn't understand how this works. Where's the mouse? Oh, okay, here it is. Okay, let's try this then. Okay.
Great. Okay, yeah, welcome everyone. Really happy to see a full house here for the CSM tutorial. This is my first one as chief scientist, so I'm excited to welcome everybody to this activity. And Cecile kind of gave you some indications about what's going to happen this week. I'm just going to say I'm going to guess that that this is going to be overwhelming, right? And that's going to be okay. Like, Earth system models are giant tools that kind of represent the collective work of 30 to 40 years of effort. There is nobody in the entire world who understands everything that's going on in their system model, and certainly nobody even in this building, and I certainly don't know everything about this model. So it is going to feel overwhelming, and that's part of the fun of it. But it's also, you'll find hopefully during this week, how incredibly powerful a tool it is to help you in research, because it is such a giant piece of software and all the infrastructure that goes around it. So I'm going to presume that a lot of you have not really thought too much about what an Earth system model is or what CSM is. So this is going to be some of this is going to be pretty basic, but I'm going to move into some, towards the end, some things that we're thinking about for the future as well. Hopefully it's interesting for everybody. Okay, so what is an Earth system model? It's a collection of physical equations that we use to simulate key fields and processes in the atmosphere, the ocean, the land, the sea ice, the land ice, every aspect of the Earth system. There are literally hundreds to probably thousands of equations within CSM that we are using to describe the planet Earth and how it evolves. It's on a grid. the number of points in the grid. There's a horizontal grid and then a vertical grid. And both the atmosphere and the ocean and the land all have vertical components to it. Our typical resolution that we run for like IPCC type simulations is about 1 degree resolution, and that's 40,000 or something like that grid points. But if we go to high resolution, it's up to millions of grid points. And so the resolution is never going to be high enough that you can represent all processes. Physical processes exactly as they exist in the world, and so anything that's sort of below that grid level is what we call parameterized. So we're going to have to come up with ways to sort of represent how effectively a process is being affected by the large-scale state. Clouds is a great example. And these build on an understanding of processes from observations and highly detailed models, process models, or things called large eddy simulations. So what does a structure look like for a fully coupled Earth system model? It looks like this. So there's generally a central coupler that handles the exchange of information between each of the different component models. And our model and most other models of this class will then have separate component models for the atmosphere, the ocean, the land, the sea ice, the land ice, and rivers, which all kind of couple together through the atmosphere. Stepping forward 30 minutes, in our case, is our standard default, but the time step depends on resolution. Calculating new states, passing that information about fluxes and states back to the coupler and then back out to the component models. And then we also, in most cases, we need to have some sort of forcing. So what are the greenhouse gases in the atmosphere? What are the anthropogenic aerosols? Or the emissions of those things? What are the volcanic eruptions? What is the solar variability? And quite a few other different forcings. So this is how we would run a fully coupled Earth system model with those forcings. And there's many purposes to these models. They're used for scientific and mechanistic understanding of past events and observed events and changes. They're used to study recent, past, present, and future projections of climate change and their impacts. They're used to study climate variability. They're used to make subseasonal to seasonal to multi-decadal Earth system predictions for societal use, and then they're used to provide actionable, societally relevant information for all different kinds of applications. And what you're probably most familiar with is the canonical, and one of the reasons we got into this business really when it became really big was when we're trying to understand climate change. And so the results from Earth system models are underpin all aspects of the IPCC report. I'm sure hands up who's heard about the IPCC report. Hopefully it's just about everybody. This is where we synthesize our understanding of climate change and provide that information for policymakers to try to make decisions. And what that climate change is or projected to be and why it's happening basically drives, not exclusively, but very largely from Earth system models. Okay, so what does CSM look like? This is the same version of that picture with the coupler with a hub and spoke kind of diagram with all the different component models. So this is CSM2, and so this is the model configuration that you guys are going to be using during this tutorial. It's also the version that we used for the coupled monolinear comparison project 6 called CMIP6, which is the coordinate activity around the world to run common simulations that are then used to write those IPCC reports. And so that happens over a period of many years, and this is the version that we used for the CMIP6 that went into the IPCC AR6, Assessment Report 6, that was released a few years ago. And many, many other simulations that you'll hear about this week, like the CSM2 Large Ensemble. And so the way the model looks, we got different components, and there's names here which are going to mean more and more to you over the course of the week. The atmosphere is called the Community Atmosphere Model, and 6 counts for the Community Atmosphere Model version 6. It's got a chemistry model. It's got a high top atmosphere version. We got sea ice, ice 5, land ice, CESM 2, ocean pop 2, surface waves, et cetera. You go around. And so this is how we track through time what each model configuration means. And it's important to kind of know what goes into these models when you're doing something like the IPCC. You want to know the provenance and the details of the model that goes into it. And a little bit more about CSM in particular in the sort of broader network of Earth system models that are around the world. And there's many Earth system models around the world, 20 plus models. There's 10 pretty big ones roughly that are of comparable size and effort and scope. There's many in Europe. China has several. There's several in the United States as well as other models around the world. But I think CSM it's fair to say is one of the world's leading models. It's very hard to say what is the best model. That's not even the right question, but it's definitely in the class of one of the world's leading models for the study of climate change and variability, and it's used really heavily in CMIP and IPCC. If you look at the literature, you'll see CSM used pretty much everywhere. It represents over 30 years of development, so these models are not built from scratch. They're very difficult to build and improve and develop, and it really represents a synthesis of knowledge that is fed up through field programs and all sorts of scientists, thousands upon thousands of scientists around the world that feed into our understanding of the Earth system and then build their ways into Earth system models. We call it a true community model. There's other models that call themselves community models. It's, there is no clear definition, but what you'll hopefully learn this week is what we mean by community is that it is an open process for model development. So anybody in the research community from the US or around the world is welcome to contribute their ideas to the model, and the best of those ideas will make it into our released version, the one versions we'll use for the next generation of CMIP models, or even some features are not used in that and they're used just for research. And also support. So one of the support is having this tutorial and also providing you support through various mechanisms as you start to get used to using this model for your own research. You're not in this on your own. We are here to help you understand how to best use your model, understand your results. And as I'll get into more, it is challenging using these models. There's a lot of community participation. We have these working groups, which I'll get into and you'll hear about more, to sort of organize our efforts across different components or different sort of features of the system. And they have several meetings throughout the year and regular meetings that you can participate remotely here throughout the year as well. More than 2,000 researchers are involved in the CSM activity at any one time, and hopefully we're going to add another 50 to 70 here this week. It's really widely used. If you go to AGU, as you are in your careers, you're going to start going to AGU. Chances are you're going to see CSM used, and I did a count just this year that there were 400 plus talks that use CSM or one of the component models at AGU in 2020. That was 2023, I should say. Yeah, 2024 hasn't happened yet. Abstracts are due today. And just to give you a sense of size, I don't know if this means anything to anybody, but it's 2.8 million lines of Fortran. Some people call it 3.6. It depends on how you count. And I say Fortran, I put in with an exclamation mark there. I'm sure it's like upsetting to all of you early career scientists to hear that it's written in Fortran. Why is it not Python? I'm happy to talk about that. Others here are happy to talk about. But basically, the overhead to change 2.8 million lines of code without introducing thousands of bugs is almost impossible. We did a quick estimate. It would take more than 100 people years to do it, probably also making the model worse in the process. There's more than 1,000 geophysical variables that you can look at from CSM. Anything you can imagine the model is probably producing. And so I like to think of it as a virtual laboratory. I'm going to sort of encourage you to be creative about how you use it. You can study so many different things with CSM or any other system model. Earth system variability and change, air quality, biogeochemical cycles, solar functioning and space weather even, process understanding, land atmosphere and ocean atmosphere interactions, ice sheet climate interactions, hydrology and ecology, Earth system predictability, weather from local to global scales, and the list goes on. So really think of it as a research tool. Okay, and I think as you're going to learn about today, Cecile kind of pointed you toward the fact that towards the end of the week, you're going to get into using more creative ways of using the model. But CSM really supports a really wide range of climate science research within a single model code base. So you'll hear a lot about the fully coupled Earth system model where we put everything together and we run these quite expensive, difficult to run simulations. And to be quite frank, that is probably one of the least commonly used versions of the model because it is so complicated, and it tends to be us at NCAR or really more senior level scientists who really have experience with this. We will be running the fully coupled Earth system model in their research quite commonly. It's definitely possible to do, but it requires so much knowledge and understanding. It is easier to make mistakes. But because it is so powerful, you can break it down and run different aspects of the model individually and in coupled to try to tease apart different aspects of what's controlling what in the Earth system. And you can then go in and make code changes and things like that. So for example, you can turn on and turn off different components and replace them with what we call a data model. So in this case, we've turned off the land, we've turned off rivers, we're just running with the ocean and the sea ice model. and connecting it to a data atmosphere model. And the data atmosphere model would give you the temperature, precipitation, solar radiation, long-wave radiation, humidity, wind, carbon dioxide, and many other fields that are needed to force the ocean model and the sea ice model. And so then you can just understand, given a certain set of atmospheric conditions, how does the ocean and the sea ice respond? Equally, you can add in, say, okay, I actually care about biogeochemistry in the ocean. You can turn on the biogeochemistry feature in the ocean if you want to ask questions about ocean biogeochemistry under observed forcing, or some idealized forcing if you wanted to. Another example, you can turn off the ocean, run the land. And I come from the land community, so this is what I do a lot in my research. I just run with the land and the rivers. So that's another feature. And then within each one of these models, there's actually a bunch of decisions you can make through turning on different levels of complexity with each one of those models. And so I'm just giving the example for the land. You can decide you want to run with land use change or not. You can run with biogeochemistry or not. You can run with crops or not. You can run with prescribed vegetation, where we're prescribing the vegetation state, or you can have a prognostic vegetation state where it responds to climate. You can turn on ozone damage to plants. That's kind of a higher order question. You can turn on methane emissions. You can change the number of soil layers. You can turn on this feature we call no anthro, which means remove humans from the system, and that's often used by like the paleoclimate community, who, there weren't humans back in the age of the dinosaurs, and so just get rid of them completely. So there's lots of, and each one of these models, component models, will have literally probably hundreds of decisions you can potentially make. Now we have it set up so that most of those decisions are made for you, but as you get more and more involved, you can make specific decisions for yourself. So I like this to show this, Earth system modeling is hard. I often use this slide to talk about Earth system model development is hard, which it really is, and that's our job here at NCAR, is to build a model for all of you to use. So you're gonna learn that throughout your career, that it's hard, and that's okay, right? It's okay for it to be hard. You're gonna learn about how to, as Cecile said, learn about the component models within CSM and the science that underpins those models. That's an important part of it. You need to sort of have at least some basic understanding, hopefully better than basic as your careers build, of what is in these models and why they're doing what they do. That's quite important. You're also going to learn the mechanics of it. How do you set up, run, and make simple modifications to CSM? And then you're also going to learn some ways that CSM is being used to address science questions. That's a really important part of your learning process. I really urge you to go to AGU, come to our workshops and tutorials, read the literature, and see how other people are creatively using the model, because that's a really big part of this, is that there is no one way to use CSM or an Earth system model. So yeah, that's just the beginning. Learning how to usefully apply ESMs and ESM data to answer research questions never ends. My postdoc advisor, when I did my postdoc in the UK, and a quite famous scientist, really well-established scientist, when I was sort of struggling in my first years of trying to use the an Earth system model, I was essentially getting results were getting out, but it wasn't like super interesting. She said, it's okay. It takes 5 years to become a good Earth system modeler. So okay, that's good. Could calm down and relax. It doesn't mean you're not going to do anything useful at all for 5 years, but to get really great insights, it could take you 5 years until you come up with your first really great study, and that's okay. So my advice is be creative, acknowledge that there's going to be missteps, and have fun, and hopefully you're going to experience some of that fun this week. And here's just an example of some of the things that we think about, and you're going to probably need to think about as you go through your careers. Different research questions require different considerations, and these are the axes that we often think about as you're starting a project, using a model. There's at least 3 decisions. There's many more actually you're going to have to make, but there's complexity. How complex of a model configuration do I need to answer the question that I'm trying to address? You kind of want to use a model that's just as complex as you need, and not more complex if you can, because if it becomes more complex, it becomes quite hard to understand your results. You're going to need to make decisions about resolution. How high or low a resolution can you get away with for how much computational time you have, and what aspects of the system are represented well at a particular resolution or not well at a particular resolution. And then you're also going to need to think about how long you're going to run your simulation for. To get good statistics, or how many ensemble members, or how many repeat simulations you're going to run to get at that question. And so, in terms of complexity, here's just an example. Climate models now have all these features in them. They've grown in complexity, and now the decision is quite complex. Quite interesting, because there are all these features in the model, and you have to decide which one of these things I don't want to turn on. And even within each one of these categories, that's a whole bunch of different things you can decide about. So that's the complexity question. In terms of the ensembles, a big thing that we've kind of pioneered here at NCAR was the concept of running large ensembles of simulations. This is where we say, instead of just running 1 or 2 or 3 climate change simulations, we're now with with a big version of the model, we're running like 50 to 100 simulations, just with small perturbations of the atmosphere, literally like 10 to the minus 15th, decimal place, and letting it run. And what you'll see is huge variability. So here are 2 projections for the precipitation trend for 2010 to 2060. And you see the wettest for the US versus the driest. So this is nothing else changed in the model. One version gives you a much wetter climate. One version gives you a much drier climate. And you need to understand that if you're trying to understand climate change, you need to understand that variability. So certain questions really require large ensembles. And then resolution. There's all different resolutions you can choose. And the cost goes up very, very quickly as you go to high resolution. So this is a really important consideration. Okay, so this is back to CSM2. This is what you're going to learn about here. But you also probably be hearing people talk about the next version of the model. We are deeply ensconced in this process of putting together CSM3, which has significant updates to all the models. We're in this painful, painful process that we go through to build the next version of the model. So if you're looking really carefully, you'll notice that the numbers increment on all these. So it looks like, oh, that's all, no big deal. They just incremented the number. But it turns out that, literally hundreds of things have changed in the model. And this is the model we're going to use for the CMIP 7, which will hopefully support the IPCC at the 7th assessment report. And our goal is to release CSM3 to the research community by summer 2025. And that's kind of my job, is to try to shepherd that process along. And here, I'm not going to go through this, just a kind of a little bit of insight into the kinds of things. These are the list of things that we have changed. It's not even anywhere near the comprehensive list of the things that have changed. So every model version, scientists like yourselves around the world say, I know a way to make this better, and then we spend, and it's about a 7-year cycle between model versions. So this is a big activity. Okay, I just want to talk a little bit about the future, I think it's kind of an exciting time to be involved in Earth system modeling, and I'm going to talk a bit about the forces that I think are driving the future of Earth system modeling. These are what you are going to be contributing to if you get involved in CSM in the longer term, because we've kind of moved from a situation where we just want to prove that climate change is happening. That was a big deal for scientists of my generation. Like, people just didn't believe it. We had to show over and over again in different ways, more detailed, that climate change is happening and how much is happening. And now what people need is an urgent need for actionable climate information. What are the climate risks and the consequences of things like climate intervention or mitigation of climate? We need to know what are the extremes, where the extremes going to change, and how is that going to affect humans with much more detail so that policymakers can affect it. And this is the kind of way I like to say it. It's like, I was at a meeting where somebody said, look, this is what it is. We need to know just these few things. Where and when will people and ecosystems experience more extreme events? Will we have enough water going into the future? And how are we going to get it? Will we be able to grow enough or harvest enough food from the oceans in the future? And can we produce that food sustainably? And really fundamentally, where are we going to put the carbon? There's too much CO2 in the atmosphere, or methane. We have to pull that out if we're going to have any chance of keeping our temperature change to 2 degrees or less. How are we going to get to the atmosphere, and is it going to stay there? Fundamentally, these are the key questions we need to address with the models. And to answer those questions, people are being more and more creative about how we can build these models and use them going forward. So we have this question. So there's those questions, and then there's also people who want to know, if you make planning purposes, you need to know what's going to happen on the seasonal to sub-seasonal to seasonal timescale, and the seasonal to decadal timescales. If you're going to start making infrastructure decisions, you want to know what's going to happen in the next 10 years. And if you're trying to make decisions and try to how to grow food, you need to know what's going to happen over this year. So out to about 30-year projections. So ideally, we would want to have a seamless system that allows us to address this. There's really an increase in demand if you're trying to answer those questions for a higher resolution. People really, if you talk to people who are trying to use these model output, everyone says around the world, and sometimes I think they're wrong in what they're asking for, but nonetheless, policymakers, people who are managing resources, they're asking for higher resolution information. We need to try to give them higher resolution information, and especially high quality information. for example, quarter-degree resolution, or even getting out to kilometer scale type configurations. There's the growth and potential of machine learning. There's not a person in the world who's not aware of the rapid growth of AI and machine learning in everyone's lives. And we know here, it's going to have an impact on our system modeling, and we're just at the beginning of that really exciting phase of hopefully really an epochal change in the ability to represent their system. And there's changing computing architectures. I told you about Fortran. We probably can't live with Fortran for forever, but we also can't afford to change. So it's a tough situation that we're in right now. And what do we need to do going forward? How do we account for the needs of code modernization to handle these new computing architectures? And then finally, I think it's really important. I was at the WCAP World Climate Research Program meeting in Kigali, Rwanda last year, where there was a really huge call for better access from around the world to ESMs, especially from people and scientists in the global south. In a lot of ways, the scientists and people in the global south are going to be left out of the conversation about climate change, and they're not able to make a contribution to it and have a say in what we're going to do about it. And they're the people who are going to be most affected. So we need to find ways to improve the accessibility of these ESMs, especially to the global south. So these drivers present a lot of opportunities, I think, and challenges for the CSM activity going out in the future. And we're trying to tackle that. So I'm not going to spend too much time here talking about this, but we do have quite a bit of effort on CSM high resolution. We've built for CSM1, we have a version model, quarter-degree atmosphere and land and 10th degree ocean that we've now run a fairly large ensemble, 10-member ensemble. It doesn't sound that large, but a huge computational effort, the biggest ensemble of simulations of this resolution that is really actually opening really new insight into the Earth system. So we were trying to build a similar version for CSM3 over the next couple of years. There's the CSM Earthworks and Storm Speed projects, which is developing a kilometer scale configuration of CSM. There's many groups around the world that are working on this kilometer scale, really, really high resolution. They're incredibly expensive. We can barely afford to run it for a couple of weeks, but it is going to be a key component of our research portfolio, probably giving the data out to you guys rather than you guys running that kind of simulation because the computational research is so big. But we are trying to get there, and many other groups around the world are doing this. And several groups around the world, frankly, are ahead of us on this. But all groups are going to be trying to tackle the real massive challenges of running at these kilometer scale resolutions globally. And there's also regionally refined configurations, and that's more of a feature that we can support, and you will hear about that this week, where we take a low resolution, for most of the world, let's say 1 degree resolution, and then you zoom down in to an 1/8 degree or even finer resolution in that central domain where you want to do your research. So in this case, it's a grid that shows for the continental United States. We can put this grid anywhere around the world. And this is a really much cheaper computationally configuration that a researcher from a university could potentially use. You can still ask some of those same high resolution questions, but in an affordable fashion. So you'll hear more about that this week, I'm sure. Moving towards what we call a hybrid version of physics combined with machine learning, there's several big projects that are going on right now that are trying to do this. There's one called LEAP, Learning the Earth with Artificial Intelligence and Physics, and one called M² Lines, which is supported by the Schmidt Futures. And both of them are basically trying to take this idea of saying, we want to say target specific machine learning, specific parameterizations in the model that we know are not, really capturing what's happening in the real world, and replacing it with one that's learned through machine learning, either learned from a high fidelity model like a large eddy simulation or a high resolution ocean model, or from high resolution observations or maybe even sparse observations of something that we don't have a really good understanding of. There's a lot of processes on land where there's not good theory. Taking that and creating a new machine learning based parameterization that we can swap into the model and hopefully get over like a long-standing bias or problem in the model to build the next generation Earth system model. And so there's quite a few activities showing there's some promise that we can maybe make a epochal change. And that's what we're focused there. But other groups are doing things about trying to create an entire model out of learning through machine learning. That's not the strategy we're taking right now. We think this is a better process in terms of maintaining understanding. And then I mentioned Earth system predictability. We have a pretty big effort moving across NCAR to really expand our ability to have a seamless prediction system to understand all these different kind of things that we want to do from a system that can work on a week to 2 week prediction or forecast system all the way out to centennial scale predictions. Okay, so I just want to finish up here by my first stab at encouraging you to get involved. So the CSM working groups really provide the platform for engaged community development and application. So we have 12 working groups within CSM. They're kind of split into two main categories. One is sort of the model development type one. So that's the land and the ocean and the atmosphere, the whole atmosphere, chemistry, climate, polar climate, and land ice, where those groups are responsible for making decisions on what the next generation model is going to look like for that component model. But they have a lot of science embedded with them as well, disciplinary science. And then we have working groups that are more focused on, using the model to, to study emerging features of the climate system. So that's the biogeochemistry working group, the climate variability and change working group, Earth system prediction working group, and the paleoclimate working group. And so these working groups are open to anybody. There's no membership. All you do is sign up to the mailing list. You can choose which meetings you want to participate in. It's really a great way to connect with scientists across the country and across the world and across NCAR who are using the model and developing the model. So it's really a great way to get involved. There's a lot of learning engagement opportunities. So there's tutorials. So you're here, 80+ of you here to learn online materials. Anyone can, if you can go back, you may notice that we kind of selected you very carefully to kind of span a lot of different institutions around the world. We hope that you're going to take your knowledge back to your home institution and help teach other graduate students or postdocs or early career scientists in the organization about how to use CSM. There's a lot of mentoring opportunities. We host a ton of visitors here at NCAR, and we're hoping that some of you will come back in future summers and spend longer time here working with us on projects. We're happy to help with that, and we also host faculty. So if you're want to come back and tell your professor about this, that we welcome faculty visits as well. And then there's the workshops. So the CSM annual workshop that we hold every year in June. This is where all the component models come together. We have about a 3-day meeting to talk about all the science that's going on across CSM, and we talk about some of the decisions we're making and the big decisions we're making on component model development. And it's a really great networking opportunity. It's 250 to 300 people come, another 100 to 150 people online. It's a really great opportunity to meet other people who are using the model. And then we also have winter working group meetings, typically in February, can be January. And these are more disciplinary meetings here, hosted here in this room usually, where scientists from, say, the land community, the ocean community get together and talk about what's going on with their component model. And that's a really great way to learn about the details or get more involved in the details, disciplinary details of a particular component model. So that's it. I just want to finish by welcoming you here to the CSM community. I hope you have a really rewarding week. I'm going to be here a little bit this morning at the coffee break, and then unfortunately I'm flying off to DC for a meeting, but I'll be back again on Friday to hopefully interact with you guys on Friday as well. So thank you, and I'll take any questions. And yeah, throughout the week, use a microphone.
Okay, I'm going to ask you to use the microphone for the question, then I will run around. I saw a hand over here.
Hi, thanks for that talk. You showed a figure on that showed the model evolving over the decades, and it was growing kind of like a triangle.
Yeah.
If you were to make that graph for this decade, how would it be expanding?
Yeah, right, because it was kind of finished in the 2010s, right?
Yeah.
Yeah, what is brand new this decade? That's a good question. I would actually change. I would change to say to what I talked about here at the end, which is it's actually a little bit less about the disciplines. We've kind of expanded into we're covering most of the Earth system now. So there's not a lot of new bars you can add to say there's a part of the Earth system that we aren't capturing. You can go in and ask specific details about specific component models. For example, in our model in the ocean, in the land model, we're not transporting carbon and nutrients in the rivers. Okay, that's kind of a detailed thing, you could add that to a specific model. But in general, I think it's more along the axes that I mentioned, which is that there's a lot more emphasis on resolution. So this kind of a big explosion of either what we call high resolution or kilometer scale resolution models. It was essentially computationally completely infeasible even 5 years ago to run at kilometer scale globally. And so that's essentially brand new, and we're really trying to learn about that maybe 10 years ago. And then machine learning is totally changing everything very quickly. And that's really a really, really big focus. And those are the two biggest things. The Earth system prediction across scales is a bigger emphasis for us. But there's been groups around the world who've been working on this. It's been more of a focal point for them, so I wouldn't add that. So yeah, it's more of a sort of a, focusing in on these sort of ways we're building the model rather than totally new science. But what is, maybe you could also say that there's some things that are becoming hardened in there. So ice sheets is on that list there, but really we only barely started running with ice sheets in the last version of the model for the CMIP 6 and the obviously AR6. In fact, most of our simulations did not have interactive ice sheets. This generation, we're getting to the point where we think we're hopefully going to have those turned on for all different simulations. So it's more of like a hardened thing, so it becomes part of every simulation. Similarly, another aspect that no model did for CMIP 6 is fire aerosol emissions. So you would think that's something you would want to do, but only a few models had fire in them, maybe about 4 or 5 models out of 20 plus models were representing fire, and none of them had taken the step to actually model how those emissions are affecting the aerosols in the atmosphere. And now several groups around the world have that capability, and we are currently in the process of making the decision whether or not we feel we can take the risk to turn that on by default. So there's sort of, that's maybe a little bit hard to, I could go into more examples, I think, but.
Thanks.
Yeah.
Is this on?
Yeah.
Okay, I have a resolution question.
Yeah.
So you talked a lot about increasing resolution and the different ways that's being gone about. Is there any effort to have the CMIP experiments, like the very basic experiments, at high resolution? Because you mentioned that they were still going to be at 1 degree resolution.
Yeah. So first thing, every modeling center gets to decide what resolution they want to run at. But pretty much everyone is still working for what we call the workhorse model. They're in the 1 degree, 2 degree, maybe there might be a group or two that's a ½ degree. So I would say one thing about resolution before I go answer your second part of your question here, or the principal part of your question, is that one thing to think about with resolution is that it always sounds better, right? Going to high resolution, but if you look at detailed analysis, we've made this detailed assessment. They say going from 1 degree to ½ degree, we actually don't simulate anything any better. So we're just spending more allocation and more more cycles, computer cycles, getting a result that's the same. You don't model any physical processes better, mostly. So we just said we're never going to go to a ½ degree resolution, essentially, global model, because it doesn't bias anything. So in terms of CMIP, there is one activity called high-res MIP, which calls for basically a 1/4 degree atmosphere, 10th degree ocean type configuration. And so we did participate in that for CMIP 6 with our CSM 1 version. And most models are trying to participate in that. They're often using the model as slightly behind their leading edge configuration, because it is such a hard model to even just to tune up, to get it to look good, because it costs so much. And so it's actually a pretty big effort to even get a good looking simulation. So, there is another activity called Diamond, which does very short 40-day simulations at the kilometer scale. And that's another sort of intercomparison project that we're trying to participate in.
Do you see, because you mentioned the progress, so even 5 years ago, we could barely run these at all.
Yeah.
Is there a point at which it will be more feasible for the working horse models to be 10th degree resolution?
We're a long ways off from kilometer scale. Doing century scale simulations with the kilometer scale, maybe in my lifetime that'll happen. Things happen, but it's a long ways off. Some groups are starting to talk about maybe they'll get their first 10-year run a couple of years from now. with just one simulation. And we already know that you need to run ensembles of simulations to really understand climate change. At the quarter degree resolution, 10th degree, that could become more of a workhorse, a couple decades. But, the computational, and architectures and things, it's sort of outside of my big wheelhouse, but chips aren't getting as fast as fast as they used to. And so now people are going to just bigger machines with more and more and more chips, or going to GPUs. And so that's requiring us to rethink how we're building these models. And that's changing fast all the time. And so it's a little hard for me as a non-computer science person to really anticipate how it's going to change. We do have teams of people here who are trying to keep track of that.
Thank you.
So how, for the CSM large ensemble, how was it chosen for to have 100 ensemble members? Was there an optimization that was done to say this is the best amount, or just what was?
There's been some research on that for sure. So we when we first did our first ensemble, I think we had about 40 members, and basically what people would do is say, you can do a pretty simple thing where you just say, let's just assume we had 20, and see if you get a different answer if you had 20 versus 40. And then you can try that across a bunch of different things. So what you'll find is that maybe for a variable like temperature, 20 would be plenty for most things, maybe even temperature extremes. But then when you start going to something like precipitation, you find that because it's so noisy, that you need to have more. And so you can just keep asking that question. You don't really know how many you're going to need until you've run that enough. And then you can try to go backwards and say, how many did I really need? And so there's research that goes into it. And I think, I can't really remember the decision why we did 100. I think it was a pretty round number. And we had the computational resources to do it. But we will this time, because we want to spend our resources on other things, we were probably going to make a really detailed assessment and ask whether or not, how many we want to do if we run a CSM3 large ensemble. And my guess is it won't be 100, but. Yeah.
Well, thank you.
Yep.
Hello. Thanks for that overview. I'm just curious about the application of ML and whether y'all feel like you're focusing more on using ML to sort of identify the sources of error and bias that we might not be getting just from our own analyses, or if CSM is using it more towards improving parameterization schemes and sort of building up that infrastructure of already known biases.
Yeah, it's both really. So we have a team of people, especially here in the climate change research section, who spend a lot of time trying to understand what's going on with the model. And yeah, they're using machine learning either to understand biases, understanding sources of biases, and also they're using a lot in prediction to say what features of the Earth system are leading to prediction. And machine learning can do a great job of trying to identify something that you can't really tell easily by the naked eye or from simple statistical analyses. So there's people doing that. That's more of like a activity I wouldn't say is it's not as organized. It's just anyone who wants to do it is free to use it. You guys are, one thing you're gonna learn this week is there's petabytes upon petabytes of CSM data out there in the world for you to use. Take that data, apply ML to it in any way you want to, and tell us about it, or don't tell us about it, preferably tell us about it. There's more data than you can but the more coordinated activity is trying to use machine learning to make the model better. And that requires just coordination in the sense that all model development requires coordination, because if everyone's doing their own thing in all sorts of orthogonal directions, you don't actually make progress. So we try to coordinate that activity. Yeah.
Hi, thanks for the introduction. I have a question for the solver used for just to solve the differential equations in this system. And I'm kind of curious, what solver is mostly used, and is there a physical limitation for the accuracy of the solver, or any efforts to try to improve the accuracy of the solver?
Yeah, so there is, so I would recommend you ask this question again to Peter Ritzen, who's going to give a talk later today. But my answer to that would be is that we are solving many different differential equations in the model. And each time, I think people are, not every time, but we're using a different solver. So there is no one solver. Definitely across component models, they make different decisions, different histories of development. And so, different solvers are being used. So there's no one answer to that. I'm also not an expert in numerical methods, so I don't really know. But there will be some sort of tolerance, right? There's usually some sort of iterative process, and we'll have a maximum number of iterations, and then you're trying to solve to some tolerance level, and it depends on which thing you're trying to solve, and there'll be times when it doesn't hit that criteria even within the number of iterations you allow, and then we just have to admit that we didn't pass it. So there is some research. I wouldn't say it's a strength here at NCAR of doing research into solvers. It's often handled by other people, and we kind of adopt them as they come online. So yeah, ask the question again to somebody who knows more.
All right, thank you very much for the presentation. Please, when you talked about perturbing the CSM model, were you referring to performing flux adjustment experiments or nudging experiments? And
yeah, that's definitely one thing you can do, right? I mean, one thing is CSM doesn't need flux adjustments, and that was a big step 20 years ago or something when we didn't need to apply flux adjustments. But if you want to do an experiment where you're trying to control things in a particular region, and you feel like that's the way you want to do it, there may be situations where doing flux adjustment would make sense. Definitely nudging. So especially in the atmosphere, that's a really commonly used way to sort of get the model into a state that it looks like the real world atmosphere, and we've used that to try to study how things are happening on land, but still allowing some interaction between the land and the atmosphere. So there's some interactions, but then you're kind of forcing the system into a particular weather regime by that nudging. And so yeah, you could ask a few people here use that a lot in their research, and it's quite a powerful way to use the model. Yeah, those are just two examples, but there's like a gazillion ways you can modify the model. Yeah.
I think we have time for one more. Yeah. After Dave will stick a little bit, and then you can ask questions, but I want to give people time to use the bathroom and to stretch their leg. But yeah.
I am curious about, you were mentioning that these future directions are a little bit more applied or providing answers to like sub-seasonal scale and longer time scales, how maybe the desire for more specific data points on like what's happening in a certain location over these time scales or at these higher resolutions is informing, aside from high resolution modeling, informing the types of development that you're doing and the types of simulations that you're going to run, just because they're looking for such specific answers rather than the uncertainty ranges.
Yeah, absolutely. Yeah, it will affect how we make decisions about what simulations to run. I make the argument quite a bit that the real sweet spot for people is going to be figuring out how to merge these sort of kilometer scale or high resolution simulations, the information we're gaining from them about phenomena, for example, like what hurricanes might do under climate change. You could run a kilometer scale simulation that, driven by sea surface temperatures at present day, and then run it again with sea surface temperatures that are, out in the 2080s. And then, to see how a hurricane might evolve, but then combining that with our understanding of uncertainty that you get from a large ensemble. And that's going to be like a really sweet spot at helping people understand what your local information is going to be. So yeah, there's a ton of decisions that need to be made. I'll just say my personal feeling, and you're going to get different answers from different people on this, is that people like to see pretty pictures, and they like to see something in their particular region, and they feel confident when they see a map that they can recognize my city on that map, and I can see what's happening. My feeling is usually when they're seeing that, the information, it's harder to understand that information, just because it looks really good, it actually isn't as good, because we don't have as good a model for that, and we don't have any uncertainty estimates. And so part of what we're doing here at NCAR is trying to find ways to communicate that to people in ways that they can understand what it means, the difference between good information and what looks like really high resolution information. And also, we're trying to help people understand the sort of the ethics of how you use these models carefully. And we're people are taking our model and all the model data from CML off the shelf and applying it to a particular application problem without having the knowledge base. And it's not their fault, but they don't have the knowledge base to understand what is useful information and what is debatably useful information. And how do we communicate to that people? That's a real huge challenge for climate science writ large. So.
Okay, you can thank Stan one more time. Then you will stick a little
I'll
bit
stick around for the
now.
break,
If you have more questions, we have a quick break. I think right now it's just coffee and tea. We will have snack at the next break. Come promptly after the break for the next talk. And if you don't know where the bathroom, you can ask the admin at the front.
Oh, thank you. I was going to bring that up.
Yeah. Okay, then the next speaker is Peter Lauritsen, but also I'm going to introduce our CGD director, John Petch, then he will say a welcome word.
Thank you. I didn't really come to say, well, of course I came to say hello. I was just coming to, so I'm new to CGD, so this is my first one of these, and I just wanted to see it in the flesh and just welcome everybody and say have a brilliant week. I hope it goes great and you learn lots of things, because there's plenty to learn, of course. I keep learning, and in my first year here, so there's plenty to be working on there. So welcome, and I won't take your, because Peter will talk for about 3 hours anyway, so I wish.
Yeah, you have a bell to stop him. Okay, then you can go.
Are we good?
Yeah, we got it.
Are we good on sound? Everybody can hear me? Alrighty. So I have the pleasure to give the first of two talks on the atmospheric component of the CESM, that's called CAM, the Community Atmosphere Model. And how many of you here have atmosphere as your interest on your badge? Alrighty, great. That's the most important component, so that's good. So it's my intention here to have you walk away from this lecture here with an idea of what a dynamical core is. And don't worry, I'll define it in a moment what a dynamical core is. How do I, the slideshow is not on my screen. I'll just talk on the first slide for half an hour then. Which way were you pointing?
This will be to advance.
Yeah,
Let's go back.
Okay, now it works. Alrighty. Okay, so here's an overview of the talk. I'll give a brief introduction to the atmosphere in terms of defining a discretization grid, and then the multi-scale nature of atmospheric dynamics, which is really, really challenging. And then I'll define what a dynamical core is and what parameterizations are. After that, I'll dive into the dynamical core that you are going to be using. That's the workhorse dynamical core for CSM2 called CAM-FV, where FV stands for finite volume. So I'll dive into a couple of details there. And then last but not least, I'll talk about newer dynamical cores in the CESM, namely the spectral element dynamical core, which is going to be the workhorse for CESM3. And then also talk a little bit about MPAS, model for prediction across scale, which is our first non-hydrostatic dynamical core in CESM. So we're in the business of global modeling here. So here's a satellite image on Earth on a lat-long projection. And the first thing we do in numerical modeling is we define a grid on which we're going to discretize our equations of motion. So I've just overlaid a regular latitude-longitude grid here, which is what the finite volume dynamical core is using. And as soon as I define a grid, I've defined a size. So the model you're going to be running, the cell sizes here are going to be approximately 100 kilometers in each longitudinal and latitudinal direction at the equator. And inside of these grid cells, we define all our prognostic variables. There will be our momentum variables, U and V, temperature or potential temperature, pressure, and all the traces we're carrying around. But I would like to highlight here that even though we've defined a grid cell size of, let's say, 100 times 100 kilometers, that does not necessarily mean that that's a scale we're accurately resolving in our modeling system. So to illustrate this, I've shown a power spectrum here. So on the x-axis here, you have scale in terms of wave numbers, so smaller waves are out here and longer waves are here, and here's how much energy you have in the different wave lengths. So if you're at large scale, it's a -3 slope. You can get to mesoscale, it's a -5/3 slope. But what you see when you run a model is that your model spectra here will start to deviate from observations from this straight line here, meaning we have less energy when we go towards the grid scale. So that means in terms of this analysis, what we really accurately can represent is typically the 4 to 10 delta x in terms of dynamics. So be really careful when you analyze your data at the grid scale, because we know we're not doing things correct at that scale from a dynamics perspective. The right-hand side plot I'll return to later. So once we have this grid defined, we're basically we've defined the resolved and the unresolved scales, more or less. You know, what's going on the unresolved scale, that's the lecture later this week. So when we're building a modeling system, we need to specify what do we need to represent in this modeling system in order to make it credible. And here's a plot from John Fuburn, representing different atmospheric phenomena in terms of horizontal scale and in terms of time scale on the x and y axis respectively here. So I'm just going to walk down the dashed line up there. So in terms of really large scales, so scales comparable to the radius of Earth, so scales of 10,000 kilometers here is, for example, the Asian summer monsoon has like a monthly seasonal time scale, and very, very long horizontal scales. Also, if you look at weather maps, you'll see the undulations and in the jet stream, so those are the Rossby waves. They are also very, very large scale. And then if we go down one scale further, we'll get into the individual cyclones and anticyclones. They have a scale of about 1,000 kilometers or so. And then in these cyclones and anticyclones, you will have fronts forming. They are the scales of 10 kilometers or so. And then we have a very complex moist dynamics going on in the model called convection, and that can be organized in a huge variety of scales, all the way from thousands of kilometers, down to 100 meters or so. When you see the small cumulus clouds forming from turbulence in the boundary layer, they're very, very small. So huge range of scales there. And then we go all the way into the boundary layer where turbulence is a dominating effect. We're at the order of like 10 meters, and all the way down to about the millimeter scale where molecular viscosity starts to kick in, so you convert kinetic energy into heating. So we would like to represent in some form all of these processes in the atmosphere. And it's important to note here that there is no spectral gap. So that means that all of these processes kind of overlap with each other and interact with each other. And that makes modeling very, very challenging. The two dotted curves that you see here, those are length-time representations of dispersion relationships for gravity waves and acoustic waves. Gravity waves are very important when there's like an imbalance in our system. We get gravity waves get emitted. So like if we have strong heating from convection, there's gravity waves propagating out. So it's a very important process in the atmosphere. On the other hand, the acoustic waves are not considered important for atmospheric modeling. The reason why I put them up here is they're really important for modeling, because if you use explicit time integration, they limit your maximum time step. Otherwise, the model can get unstable. So you really need to pay attention to these fast waves for that reason. Okay, we can get it to advance. There we go. Alrighty, so the shaded area up here, that's pretty much where like IPCC general circulations operate. So they're about this 100-kilometer scale that I mentioned above here. So we're really only resolving a small fraction of all of these phenomena in the model here explicitly. We do have efforts now in terms of the global model to go all the way down to 3 kilometers. So in that case here, we would start getting into this area here. So you'll start resolving large cumulus clouds, and deep convection will be explicitly resolved in those configurations, but they're very, very expensive to run. Alrighty. So in terms of our model code, we have a very clear separation between resolved scale and unresolved scale. The resolved scale here, that's where we solve our dynamical core equations of motion, and basically everything we can't represent in the dynamical core, we throw into the parameterizations up here. So that's where you will have, at least in large-scale model, you have a deep convection scheme, you have a shallow convection scheme, condensation, radiation, turbulent mixing, etc., etc. And these two components need to be coupled. And there are several ways to do that. It's actually a science how you couple the parameterizations with the dynamical core. And there's actually it's kind of an emerging research subject. There's even a workshop dedicated to it called physics dynamics coupling. But basically you can update your tendencies from the parameterization with the dicore in 2 different ways. So one is you let them start from the same state, so parameterizations and dynamical core start from the same state, you integrate them forward, and then you combine the 2 solutions. The other way that the modeling system you're going to be using is time split. So that means you start out running the dynamical core, update the state, and then you give that state to the first parameterization. So that's usually a fast parameterization like convection. And then you update the state based on that, and then you march forward in that way. And if you change the order, you get a different solution. Alrighty, so that was defining the grid, looking through all the different phenomena we would like to represent in the model. Now I'll get a little bit more specific. So as I mentioned, we're going to work with the finite volume dynamical core. It's defined on this lat-long grid here. And in the exercise you're going to run, do you specify the dynamical core you're going to run in terms of this resolution notify here. So if it's F09, MG17, you'll be running our standard CESM2 configuration with the FV dynamical core. In terms of the vertical coordinate, we're using what's called a hybrid pressure vertical coordinate. So it's defined in terms of the surface pressure. So you see here our model levels, our interfaces that are denoted by K plus a half are defined in terms of the surface pressure times a hybrid coefficient, and then a model top pressure, which is about 2 hectopascal, times this other hybrid coefficient. And near the surface, B is 1, A is 0. So that means you're completely terrain following near the surface, and then you slowly transition into pressure levels. And we do that to simplify the bottom boundary condition. It's a lot simpler when you're terrain following compared to when you're not. So FV uses a terrain following coordinate, but on top of that, it also makes it Lagrangian. So that means we start out with the hybrid coordinate I just showed you, and then we'll let the dynamics evolve with the assumption that there is no mass flux through the model level. So that means if you have convergence, the model level will expand. Divergence, it will contract. And then every so often, every half an hour, once these surfaces have started deforming, then we map our variables back to the reference pressure. So that's what's called a Lagrangian vertical coordinate. We use that in FV. We also use that in our newer dynamical core called spectral elements. One advantage of doing this is that you're just solving 2D problems instead of 3D problems when you're doing this. So you're basically solving stacked shallow water equations if you're familiar with those. In terms of vertical extent, CESM supports a lot of different configurations. So you're going to be working, I think, mostly with CAM. That's the low top version of the model, where the top is about 42 kilometers. I know I wrote 40 here, but I think it's more like 42. Wacom has a top at 140 kilometer-ish, so you have a well-resolved stratosphere. And then we have a geospace configuration of the model with a top all the way out in space at around 600 kilometers. And again, as you go up through the atmosphere, you have to represent different processes. So the model physics will change with these different configurations. In particular, if you're focused on the dynamical core, the Wacom X is more challenging because now you have species-dependent heat capacities in the dicore, you have molecular diffusion, et cetera, et cetera. Just as a note, in our new model versions here, we've moved the top up to about 80 kilometers and increased the number of levels to 93, so more similar to what most global modeling groups are using. But we're also keeping the low top version around because it's a lot cheaper to use. Alrighty, so that was a grid, horizontal and vertical extent. Now I'll dive into the actual dicore, but just briefly. If we take the most unapproximated set of equations called the compressible Euler equations, they will be pretty complicated and very expensive to solve. So therefore, in large-scale modeling, we do a series of approximations to make this system simpler. And actually what's happening right now in the dynamical core community is we're slowly getting rid of all of these approximations in the modeling system. But this is what's done in FV. So first of all, loosely speaking, we assume that Earth is round. Gravity will only act in the radial direction. We know that's not really true. Earth is a little bit squeezed, and gravity is a 3D variable. But that's a pretty accurate approximation. We made what's called the quasi-hydrostatic equation. That means that your vertical velocity is diagnostic. You assume that the vertical velocities are much smaller than the horizontal ones. A lot of people here would argue where that starts, but I think there's some agreement that it starts around 10 kilometers. And then we make what's called a shallow atmosphere assumption, again, to simplify the system of equations. And every time you simplify an equation set, you have to make sure you conserve key quantities in the system. So this shallow atmosphere approximation is a series of approximations where we make sure we still conserve energy and angular momentum in the continuous equation of motion. So if you make all of these assumptions, assume a vertical coordinate, a Lagrangian coordinate, then you get this system of equation here that FV is using. So you have a continuity equation for mass, you have one for tracers, you have your horizontal momentum equations, and then you have a thermodynamic equation. I will not dive deep into these equations other than the continuity equation, just to give you an idea of what finite volume the finite volume dynamical core does to these equations. I'll just concentrate on the continuity equation. So what you do in a finite volume method is that you integrate your equations of motion over a volume, hence finite volume. So that's shown up here. Pressure is the vertical coordinate, and horizontal, we got our lat long coordinate system. So if you do that, so if you integrate the equation of mass over a volume, you get that equation there. And then we use Gauss's divergence theorem to convert this volume integral into a surface integral. So that's what's written here on the right-hand side. And if we go in and physically analyze what that actually means, it simply says that the change of mass inside of my volume, that's the ddt of this term here, is equal to the instantaneous flux of mass in and out of that volume. Very intuitive. Then we can then discretize our system in time, which is done in equation 3 here. So it simply says, new mass minus old mass should equal the flux into the volume. Just to give you a graphical or a visual graphical illustration of what this is all about, instead of talking about equations, you can look at this figure here and then assume that you have a flow so that this gray area here after one time step ends up at the regular grid cell up here, which is a little hard to trace out here. So it's a Lagrangian volume. No, there's no flux of mass in it. It just moves with the flow. Like you're throwing a fishing net out into the river, it will just move with it. So what you're doing in a finite volume method, that's Eulerian. Let me just go back one step here. So all these yellow areas, they get swept through each of the faces of this cell. So like this cell, the bottom side of the cell, this area of mass will get pushed through, and similar for the other ones. And if you add up all these yellow areas, you exactly get the full Lagrangian form. So what you're doing in an Eulerian flux form discretization here is that you somehow want to approximate these yellow areas here. And how you do that, I won't go into detail, but it's based on a scheme called the Lin-Root scheme, which has been widely used in modeling, which is a dimensionally split approach to approximate these yellow areas. So this is what it looks like in terms of formula. I won't go into further details. And the other equation of motions I won't go through. But just get back to my earlier point about the grid scale. So these equations of motion here, they're very noisy unless we somehow control the divergent mode. So we add this numerical dissipation term to the system. And on the next slide here, I'll show you why. So this is an example from a half-degree equation where you don't have this divergence damping term, and you see you get this hook in the energy spectra. And if you look at the actual solution, it's very, very noisy at the grid scale. So therefore, we add these explicit diffusions, and then you get the tail of the spectra to be well behaved. And all models, all die-cores have some kind of control at the grid scale that will damp these wave numbers more than they're actually damped in, quote-unquote, damped in nature. Alrighty. I have 7 minutes left, so just at the very end here, in the last 20, 30 years or so, there's been a true revolution in dynamical core modeling. And the reason is, as you probably can guess, the emergence of massively parallel computers. And the problem with the finite volume dynamical core, as well as spherical harmonic models, if you're familiar with those, that's what ESNWF uses, and other modeling systems are still using them. They're about 40 years old at this point. The problem with these methods here, they don't work very well on massively parallel architectures. And the reason is for the spherical harmonics is you need to do a Legendre transform, which is a global operation. The problem with the finite volume dynamical core is that is the poles. You have this convergence of the meridians near the poles. You have to apply filtering, and again, that implies non-local operations that have to take place. So if you look at how well we do when we scale out an application, here it's a pretty old plot, but it still illustrates the point. On the x-axis here, you have numbers of cores you're throwing at the problem. So from about 1,000 cores to 64,000 cores, and up here you have throughput. So that's simulated years per day. And what you see with the spherical transform model is as you throw more cores at the problem, it kind of levels out. And if you throw even more of them, you even get less throughput, which is definitely not ideal. I should mention, like, the perfect scaling would be this straight line here. Like if I throw twice as many cores at the problem, I get my solution twice as fast. The finite volume dynamical core is here. at quarter degree. And as you see here, as you scale it out, it starts to fall off. Please keep in mind here, these plots here depend on your problem size. On climate modeling, we're very, very challenged because we really want to throw a lot of resources at the problem to get our solution faster, but we don't have that many degrees of freedom. If you go to 3 kilometer model, you have so many grid cells that even if you run on the largest computer on Earth, you're probably still in the lower part of this scaling curve here. If it was finite volume, you'd be sitting down here. You wouldn't even get close to having this thing fall over. So keep that in mind when you look at performance of models. So weather modelers are not as concerned about this as climate modelers are in general. A way to get things to perform well on these massively parallel systems is you use a grid that's quasi-uniform. So for example, you can use the cube sphere here, where all the grid cells are more or less the same size. You can also use what's called a Voronoi grid, which is shown over here. Then there's another grid that's a little less popular. It's called the yin-yang grid, where you take 2 lat-long grids, chop off the 2 poles, and then glue them together. But by far, the cube sphere and the Voronoi or icosahedral grids are dominating right now. So we have several dynamical cores defined on these newer grids that scale pretty well. So we have the spectral element dynamical core that I mentioned we're going to use for CSM3 applications. For CSM2, it was used for high resolution applications and mesh refinement applications. And then we have MPAS that's being integrated into CESM3. And then we also have, but with very limited support because funding ran out, we also have FV3 that's used by NOAA for operational global weather forecasting. There'll be a talk later this week. It's a very popular application of our modeling system is to do mesh refinement, meaning you have higher resolution in some region of interest. So here's an example for the spectral element dynamical core. This is called the CONUS grid, where you have high resolution over the contiguous United States. And here's another example using the Voronoi, the MPAS grid, where you have mesh refinement in this area here. So Adam Harrington will talk about that later this week. Alrighty, I have 2 minutes left before Cecile gets upset. For those of you who are interested, let me just spend 2 minutes talking about the spectral element dicore, because it's fundamentally different than a finite volume method. So the finite volume method we were integrating or integrating the equation of motion over volume. This is a Galerkin method. So here I'm going to project my solution onto a basis function. So that's kind of what I've tried to show here. So first of all, I like to describe the cube sphere like this. You put this Rubik's Cube in here, you inflate it, so it spans the sphere, then you get this grid. And then inside of each of these quadrilaterals here, you have a computational space that basically looks like a lat-long grid. And then inside of each of these, you define a quadrature grid to perform mathematical operations on your basis functions. And in this case here, we're using degree-free Lagrange polynomials that look like that. Like this. So it's really fundamentally different than a finite volume method. The really nice thing about it is it's a very, very local method. And it's also coded up a lot more cleanly than our current finite volume core. Alrighty. Another feature in our CSM3 modeling system is that we decoupled the physics grid, where the parameterizations are running, from the tracer grid, from the grid where all the UVTP, the basic dynamical core variables are operating. So in the CSM3 model, it looks like this, where you have the tracers here running on the same grid as physics here, so they're all approximately 1 degree. But it does open up for the possibility if you want to explore it. So for example, DOE is using this in their quote-unquote operational system. They run physics on a 2x2 grid. So if we're running a 1 degree, our 1 degree model with a 2x2 grid, you would run physics on approximately 1.5 degree grid. And the nice thing about that from a computational perspective is instead of having 9 cells here, you only have 4. So you're cutting your computational expense of physics by pretty much, well, by more than 50%. And physics is very expensive, so it is a way to get more throughput. You can also run in a finer grid if you wish to do so, vastly increasing the computational cost of the model, but there are some scientific issues you could explore by doing that. Alrighty, if you're more interested in how to build global models, we had a colloquium here. Oh gosh, it's a long time ago. It was back in 2008. But there was a book coming out of this, and no worry, I don't get any money if you buy this book. But it kind of goes through all the deliberations that go into building a dynamical core, and those deliberations have not changed, but there obviously have been major advances in building systems in the last, or since 2008. But there's a lot of great chapters in there if you're interested. And if you're interested in just the numerical method aspect of it, I really recommend Dale Duran's group, Numerical Methods for Fluid Dynamics. And he actually updated this book here to cover Galerkin methods. So both continuous and discontinuous Galerkin methods, which are pretty popular. The Navy is moving towards that. We are using it. DOE is using it as well. So if you're interested, buy that book. It's not bedtime reading, though. It's pretty hardcore stuff. Alrighty, I will take questions.
Thank you so much, Peter. Then, question for Peter. Okay.
Thank you for the introduction. So I'm just curious, like, so you mentioned that those numerical methods will all introduce some mismatch of the kinetic energy spectrum with the real spectrum. So will that introduce any problems if we say, like, in terms of like when we add a forcing into the systems, a forcing of energy into the systems, will that introduce any problem that this mismatch happens? Yeah.
I wish I knew the answer. So what we're doing is we're hoping for the best. A motivation for looking into that was actually this physics grid I just showed here. This is a pretty old idea that came out of University of Reading by Brian Hoskins back in '97, because he said, I cannot trust a grid scale. I can trust 4 delta x maybe. So I should only give the 4 delta x wave to the parameterization so I know that that's right. That's what you would try to do with this method here. Our experience is if you use higher order methods to move variables between the grid, we could pretty much match in aquaplanet simulation, simplified setup, we could pretty much match the solution of this grid here with this grid. So we made the model, since physics is about 50% of the model runtime, we made the model 25% cheaper, but got the same result. But that's a simplified setup. We run the land model on the same grid as the atmosphere. You're also coupling to other components. So there might be some decremental effects to going to a lower resolution grid, because topography, for example, which we do know where it is, how high it is, would not be as well resolved. And similarly, land model won't respond at that scale as well. And in fact, we've seen a degradation of our polar climate by moving to a more isotropic grid. So now we have a physical scale of about 100 kilometers over the poles. The lat long grid has really high resolution up there. In terms of just simple dynamics test, we're as good or better because we don't have a problem. But since we're coupling to the surface component in like 4, 5, 6x more points, we're getting a better solution than running on a coarser grid. So I hope I'm not confusing you here, but it gets really complicated really fast. But it's only NCAR and DOE that have explored this 2x2 physics grid. And DOE went with it for operations, I think mainly for computational regions, and we're sticking with the 3x3 physics grid.
Great. So you talked about the different schemes that give you higher throughput for parallelization. I was wondering, and maybe you were getting at this a little bit, but I was wondering if some of those different schemes make the parameterizations more difficult, or you have to be careful about like where you're parameterizing stuff. Like, is there, with variable resolution, I can imagine in some places you're able to resolve more, in some places not as much.
Yeah, are you referring, because, so one aspect, I'm not sure if that's exactly a question, but like we used to call physics in these grid points here, this quadrature grid. So that means you have like I don't remember the numbers, like 150 kilometers between the two middle ones, but then you only have 60 kilometers for the other ones. And in idealized experiments, the aquaplanet ones, we're seeing artifacts due to that. And also that the basis functions, I didn't get into this, but you know, they only see zero continuous at the edges. So that would create like spurious precipitation and so on over those points. So that was why back then I proposed, you know, we should really run physics on this grid here. So we're integrating the state variables over these control volumes and then passing that to physics. So that's one aspect with the Galerking methods. Was that what you were thinking about?
I guess so, especially the variable resolution models, that I think is another part of it. Like, how do you deal with having a coarse resolution? And then, like, because I imagine the parameterizations, I just can't imagine that they could be exactly the same and have it work.
That's a grand challenge right now, especially because a lot of our parameterizations were developed with grid spaces about 100 kilometers or so. So if you look at deep convection, it has the statistical assumptions in there that your updraft will only take up a very small part of your cell. But then when you go to 10 kilometers, it's not quite the case yet. So a big buzzword right now is like scale-aware parameterizations that will, you know, that are able to go through this transition zone where you go into the mesoscale, and it's a very hard problem.
And then
some parameterization will adapt automatically, and others will not.
Okay. Another question more related to like the user friendliness of these sorts of models. Are there people working on, like, if I wanted to run something like this and then compare it to output from a more standard grid, like, is that sort of comparison something that's easy to do or something you'd have to figure out on your own?
Usually we map variables to a lat long grid,
okay,
and then just compare them.
Okay.
And in terms of setting up simulations, like Adam will talk about that, we put a lot of work into to document the process, and it's not straightforward. There's a lot to think about when you make these grids. So there's a lot of information on it, but there's still a little bit of, it's good to have an experienced person look at the grid, because sometimes you can create a grid that has a tiny grid cell and then the model will blow up. So there's a little massaging that's necessary. I'm sure Adam will talk about that.
Thanks for a great session. I adopted mesh findings in CESM. Not, and what is the biggest
Yeah, so 3D or even 2D mesh refinement is a really hard problem in a full model. So there has been efforts in DOE to do fully 3D mesh refinement. I'm also working with colleagues up in Canada just on 2D mesh refinement. The big challenge is, like, what is your refinement criteria? So when you're running idealized simulations, it's pretty easy to find, like, you're gonna just mesh refine around this front or something like that. But when you're running a full climate model, it's really hard to tell where you should refine. And then the other thing is how your parameterization is gonna respond to that. So similar to the other question, if all of a sudden the grid scale gets really small, you need to shut off deep convection as an example. And the other thing that's going to happen when you refine is, what do you do with topography? Like when we increase the resolution of the model, we also allow topography to go to higher resolution. So when you go from low resolution to high, your topography starts growing upwards. And if you do 3D or 2D mesh refinement, all of a sudden your topography is moving like this, which is pretty toxic for a dicore, because it will. A dicore will always try to get back into balance. No? So if you all of a sudden increase the elevation by a couple of hundred meters, it will emit gravity waves and so on. So there are really big challenges in full modeling systems. But I won't say it's off the table. There are just a lot of challenges to work through. And I think the benefits could be immense if we can get it working. But I think the big challenge now, get the static mesh refinement under control, and then we can really start thinking about dynamic mesh refinement.
Any more questions? Otherwise, Peter will stick a little bit. Are you fine to stick?
Yeah, now
a little bit
for the sessions.
Yeah, and he will be around during the lab session. Then, yeah, if you don't have any more questions, we are going to move to the snack. Then please be efficient. There will be a table, and you can go from both sides, and there is some coffee left. Because as a reminder, you cannot bring back food here. Then you have to eat everything there. You can bring your coffee or your tea if you have a top on the cup. Thank you. Where is my other microphone? Oh, yeah. Okay, then we are going to move to the next presentation. And we have here Rory from the Supercomputer Center, CESL. Oops. Yeah, then he's going to give you a lot of important information that you will need to run the lab about the supercomputer.
All right, good morning. I assume this is working out there. So the nice thing about this talk is after Peter's talk, it should be pretty simple to comprehend. So it's good to do it in this order. It's almost like a little break before you get to the lab session. I am an HPC consultant, so there's a group of us here that basically help folks like you that are trying to run models on the computers. We help with the computing side of that. So the most important part of my talk is this first slide. And this is really outside of this tutorial, how you can get help if you encounter difficulties. Also, at any point during the tutorial, you could do these things. So our main documentation is at ncar-hpcdocs.readthedocs.io. That's kind of the root page of everything. Some important links I'm going to call out here. Getting help, if you click on that, it'll take you to a page telling you who the consultant on duty is and how to contact that person. This is how you could submit a ticket at that NCAR Research Computing link. So if you had a problem with your account or something like that, or just a question about the computer, you can submit a help ticket on that. And another important one is if you have problems with passwords. So my group actually has very little visibility into the password problem thing. That's more of a broader NCAR service, not a supercomputing service. So you can call that phone number, 497-2400, and or there's a help desk downstairs. So if someone has a problem today, I can physically take you down to where that help desk is. And they are usually the people that can solve password problems. Okay, so things I'm going to talk about, just the systems we have, how to use them, how to sign on to those systems, the software we have and how to use it, how to manage jobs through a batch scheduler, and just a tiny little bit about customizing your environment. You don't really need to remember anything from my talk. I'll be around all day today. I'll be around again on Friday, and one of my colleagues will be around likely on Tuesday, Wednesday, Thursday, and I'll be available sort of virtually all week. So you can ask me things at any point. I'm going to quick overview of the main system you're going to use this week. This is a system that we've had just for about a year now called Derecho. It's an HPE Cray system. 2488 CPU nodes, which are what you'll be using. It also has some GPU nodes on it. I think a broader point about what makes a supercomputer these days, if you've not used a supercomputer, honestly, they're largely like 90% the same parts you would get if you went down to Best Buy and you just give me a computer. There's nothing too special about them except the things that make them super are the plumbing. So they're water cooled and have kind of, actually, in fact, not even water, fancier than water coolant, PGW. So fancy liquid-cooled cooling systems. They're very, very dense. You can think of each one of those cabinets as being sort of refrigerator-sized, but much taller. I think each one of those things weighs a little over 8,000 pounds. And they're very densely packed full of computer stuff. So really, the plumbing that keeps them cool is part of what makes them super. And the only other thing that really makes them super is the network. And the network is a proprietary thing that's pretty fancy. It's an extension of Ethernet that HPE came up with called Slingshot. And so each one of these nodes has 128 CPU cores on it and one of these Slingshot interfaces. And it's arranged in a topology that is called a dragonfly, but it's basically a way to make a big system with not many optical fibers. Because that's one of the things that makes computers expensive, the supercomputers, is the cables themselves are very, very pricey. So it kind of minimizes that cost in a big computer. Like I said, it does have some GPU nodes on it. You're not going to be using those for the workshop, but maybe at some point at NCAR, you'll get a chance to use the GPU nodes as well. The other system we're going to be using is called Casper. And so Casper is a much smaller system. In my mind, it's also much, much, much more complicated than Derecho. It's like Casper is if you went down to Best Buy and you bought one of everything and then duct taped them all together. It's kind of been a homegrown system. We add onto it in phases and take away from it in phases, but it's really heterogeneous. So this slide's probably not even right. I didn't put too much work into fact checking it, but you can see there's a lot of different node types. So there's 22 of these nodes that are meant for data analysis and 18 that are meant for large memory GPU codes and then subcategorizations of those, et cetera, et cetera. So Don't worry too much about the eye chart that is Casper. Just know that there's a lot of different types of resources available on it, and we'll be using one type of resource as far as I know, which will just be those data analysis nodes. Okay, so probably the most important thing about using the supercomputer is being able to access it through a terminal. Out of curiosity, how many of you are regular terminal users these days? Okay, good. Most of you. So SSHing in, you would do SSH-X-Y. That's the X and Y are optional. That's only if you want to do X Windows stuff. There are other ways to do graphical things from the supercomputer. So if you don't want to use X Windows, you don't have to use the XY. But SSH-XY optional, -L your in-car username, dirhj.hpc.user.ucar.edu. There are 8 login nodes, and you'll just get shuffled between one of the 8 in a round-robin fashion. And if you have authenticated an in-car before, I'm not sure if you all did that at some point before today, but if not, you'll be doing it for the first time today. You go in, you type in your password at the prompt, and then if your password was correct, your phone will get a push notification, and you'll accept that. And then you'll be logged onto the system. So it's kind of a 2-phase thing. And I want to call out a separate way to authenticate if you cannot get a push notification. Some people have poor cell phone coverage in this building and can't get a push notification. Sometimes the network itself is busy doing tutorials and you can't get a push notification. So when you open up the Duo app, there is a little passcode. When you click the UCAR part of the Duo app, it takes you to a screen with a passcode on it. That passcode changes like once every 30 seconds. But you can do the SSH, you can type in your password, and then a comma, and then that 6-digit passcode that's on the Duo app, and that will skip the push notification part. So that's, I know at least on Friday, I'm going to try to get everybody to authenticate that way, because on Jupyter Hub, which we'll be using on Friday, that's a particular help.
And I want to say there is instruction how to do what he just said about this password, passcode in the documentation of the lab. Then if you don't find it, call us.
Okay, and then I'm going to quickly talk about other ways to run GUI programs. That's because typically if a lot of you are showing up with your own laptops or things like that, not everyone has X installed. Usually there's someone who doesn't have permission to install X. So we have a couple other ways you can do this. You can use a VNC client. This basically is, the advantage here is it's faster and more responsive than X Windows. You do need to be able to install a client as your user. So if you are able to install a little piece of software we have on our website, you can install this client, and then there's you log into the system normally and use this command called vncmgr, and it will basically get you a desktop onto the system. Another way to do that if you cannot install software is through the service we have called FastX. And FastX can be entirely browser-based if you're not on our VPN. So most of you that are just visiting students for this class, probably you're not on the VPN. You have to do this slightly more complicated way of authenticating through an SSH tunnel to FastX, but it's still possible. So you can just use a browser to get graphical displays back from the system if you want. And that's all you need to take away from this. If you actually need help doing that at some point, come find me and I can help you get set up. Jupyter Hub that we'll definitely be using on Friday. So I'm going to walk through the process here of how do you get on Jupyter Hub. So you go to jupyterhub.hpc.ucar.edu. You'll see a little button that says production. Click, fill in your normal system username, so the one that was assigned to you, the same password that you would use for a Duo push, but like I mentioned here, doing the password comma passcode thing would be the preferred method for Jupyter Hub. Then it'll take you to a screen like this. If you don't have a server running, you'll see the option to start a default one. Click on that, and then it will ask you for some resources, which I assume, Cecile, you probably have some. Is there any recommendation on that, or are they just doing the defaults that get filled in? Okay. Probably it's sufficient just to do the default workload, which is like asking for a single core on a single node, I would assume is what you're using. So you won't need to touch that much. You click the blue button at the bottom. Oh, probably the one thing you will need to touch, it does ask you for the type of, after you click on that, it will ask you for the type of system you want access to, and you see the box up there that's yellow. Casper PBS batch is what you'll be using. So And then once you're on the system, it'll look like this. This is also, there's a lot of different, so ways to do Python notebooks, R, Julia, the sort of typical analysis tools. Another thing, if you are just looking to get to view output from your plots earlier this week and you don't want to go through the trouble of installing X windows and stuff, you can also usually just click on images in Jupyter and get quick looks at plots and things like that from the system. Okay, this is just kind of a reminder that on the login node, so when you first access the system, you are not in like a node dedicated to yourself, a compute node. You're in a shared access environment. So just try to limit your activity on those login nodes to simple things. So don't try to run CESM on the login node. Makes other people kind of miserable. And actually, these days, what will happen is we have some automated processes that are watching activity on the login nodes. And if you start doing something that's too computationally expensive, it will kind of ratchet down the amount of resources your job is given or your process is given. So the login node will start to feel really slow to you. And in extreme cases, your process will just get killed. So it's not, it's not that harmful to do, but it won't be fun for you more than anything to try to run something expensive on a login node. If you get an automated email from something called Arbiter, it means you've done a bad thing. It'll tell you that. A little bit about the file spaces we have. So your main home directory, when you log into the system, with the directory you'll be placed in, is 50 gigabytes large, and that directory is backed up. So if you have anything important that you want to keep a hold of, that's the place to put it because we back that stuff up. It's not a very big space. It's only 50 gigabytes, but we do have some other spaces. So there's a workspace, which is /glade/work/your username. That's quite a bit bigger at 2 terabytes. We don't back that stuff up, though. So if you accidentally delete something out of there, you'll lose it. So things that that you might put there are things like that you check out from GitHub and regularly check back in. So think of it as like a working directory, but stuff that's there, you shouldn't be heartbroken if you lose it. And then a much larger space is your scratch space. And think of that as like a really temporary workspace. So it's quite big. It's 30 terabytes. And not only is it not backed up, though, we automatically delete stuff out of there for you, even if you don't ask. We do that every 120 days. So if you write a file there and you don't do anything with that file, 120 days later, it'll get deleted. So don't put anything important there. But it is a place where you keep model outputs and things like that. CESM is already configured that when you do a model run, that's where it's going to write your model outputs to. And then there's another space, Glade Campaign, and that's kind of allocated to projects, not to people, and it's done by request. So if you're working with someone in NCAR, you may already have a campaign space, but you won't need it this week. To get data on and off the system, if you just have like a little bit of data, text files or a few megabyte type data, even a gigabyte, if you want to transfer it with SCP or SFTP, that's typically fine, but it's not a fast data transfer method. So if you're transferring like large data sets in or off the system, we recommend using Globus. That's just kind of a graphical and or command line way to efficiently transfer large amounts of data. The advantage of Globus is like you can translate, if you're transferring a 2 terabyte file and your computer dies in the middle of that transfer, it's okay. You can reinitiate the transfer and it'll pick up where it left off later on. And it's much faster too. So that's just, you don't need to understand how it works today. You just need to know it exists in case you have questions about it later. We can get it set up. Okay, environment modules are kind of the way you access the software that's on the system. It's just basically a method. You've hopefully used them at maybe another institution, but basically a way of just ensuring whatever your user environment is, whatever software is in your environment is sort of mutually compatible, because we have a lot of different compilers and libraries and things, and you can mismatch them in really toxic ways. So if you're only using software through the environment modules, then it makes sure whatever you're using kind of all plays nicely together. And just a note that Derecho and Casper, because they're quite different systems, the module software is a little bit different between them too in terms of what we offer. We try to make it similar, but it's not always possible. Like Derecho in particular has a lot of proprietary HPE stuff that we can't have on Casper. So these are the commands you would need to know about to manage your environment. Module load or unload would add or take away a piece of software from your environment. Module avail shows you anything that you could load. And that list changes depending on what you do load. That's what I mean by that. It's kind of checking to make sure everything plays nicely together. So module avail looks at what you have loaded and tells you what you could load that would be compatible. Module list shows you everything you have loaded. Module purge would remove stuff. And I say module, this is in parentheses, that dash dash force. Dash dash force means get rid of everything. So by default, there are certain kind of like really base levels of the module system that are sticky. And if you purge stuff, those will still be around. But if you really want to blow everything away, you can do that dash dash force. Save and restore. Well, if you load a certain set of modules you really like and you use a lot, you can say module save and then some name, and it saves that whole set. And then later you can say module restore that name, and it will kind of reload that whole environment for you. Yeah.
How is purge different from unload?
So unload unloads a single thing. So you'll see like module unload software. So like I would say module unload Intel. Whereas module purge, you just say module purge and it gets rid of everything, except for the sticky things. And for the sticky things, you need the force. And then module spider is kind of the way that you search the module tree. So module spider, then some keyword, and it will tell you all the things that contain that keyword or that are related. On the diagram on the right there is just kind of showing like a workflow. So the big pink box is one of those sticky base modules that I've talked about, NCAR-N. So that's like we release those around twice a year. It's a whole set of software. That's always loaded for you, and then it gives you access to, for instance, the beige box, things that are in the category of compiler. And if you were to load one of those categories of compiler, like the Intel One API compiler, then it takes you to that middle box, and it says, okay, now the Intel compiler is loaded. You now have the option to do things like load an MPI library, which is a whole other category, or individual pieces of software like NetCDF. And then if you load an MPI library, it says, okay, well now you have an MPI library loaded and a compiler loaded. Now you have the ability to load parallel NetCDF, for instance. That's just kind of how that workflow is. It changes as you continue to load or unload things. So the things you can do through there, the main categories of software, compilers, debuggers and performance tools, MPI libraries. I have some stars up there next to all the MPI libraries except for Cray impitch. At this point, you should consider Cray impitch to be the only one that actually works. The others are all kind of in experimental mode waiting for HPE software to make them fully functional. IO libraries, NetCDF, PNetCDF, things like that. Analysis languages, so Python, et cetera. And then convenience tools, so like NCAR compilers. You probably won't need any of this stuff this week because the tutorial is going to be managing a lot of this for you. But there are some just convenience tools in there as well that you might need beyond this week. So interacting with the compute nodes now from a login node is all done through a batch system. We run PBS as the batch system. The basic workflow here, the gray box on the bottom, that's the workstation. You SSH in either to Derecho or Casper. Now you're on a login node. From a login node, you want to run a job on a compute node, either a Derecho compute node in the blue box or a Casper compute node in the purple box. And you do that all by asking PBS to run something for you. Basically what you're doing is you're telling the batch system, I want to request these resources, so like whatever, 500 CPUs. And I want them for this amount of time, like 6 hours, and I want them on a specific type of hardware. So not just any CPUs, but I particularly want like like on Casper, there's probably 15 choices you could make. And then the batch scheduler goes out and it says, okay, where can I find the resources you want for the right amount of time? And it grabs them for you and then dedicates them to your job. When you're running that job, you're burning core hours in a project. And there's a website called sam.ucar.edu, where you can see how much you've spent. And a note at the bottom there that temporary files often get written during like the execution of a model, so you just want to make sure those are getting placed in your scratch space. By default, unless you've done something to your environment, this variable should be set for you, but we see a certain number of jobs fail that way just because that's unset. So if you get a word failure, that's something to look at. This is an example of a batch script. Again, CESM is going to create and submit these for you. All the sort of scripting infrastructure around the model creates these. So you don't need to edit these directly, most likely this week, but this is just kind of like a look behind the scenes, how the sausage is made. The components of a bash file, all these lines at the top that start with #PBS, those are all things you're asking the batch system to do. So you can say that -n is what I want to call my job, hello_PBS. That's just like a note for me so I can identify my job. A is the project you're using, so where your charges will go. This -J and -K, OE and EOD, that's just put those in your batch script. It's like a nice way to make sure the output gets written and doesn't disappear. The Q you would be using is on derecho, it will always be main, and on Casper, it will always be Casper. There are other options, but you won't really need to use them this week. Wall time is like the length of time you're asking for resources, and then that select statement at the end, the way that breaks down like that there, I'm saying select equals 8:, NCPUs 128, MPI procs 128. That's a fancy way of telling the batch system, I want 8 copies, like 8 nodes worth of 128 CPUs on each of those nodes, and start 128 MPI tasks on each. Then later in my batch script, now that I've asked PBS, I've told it what I want, now I'm saying, okay, now that I have that stuff, here's what I want you to do. I'm setting that temperature environment variable that I mentioned before. Again, that should be done for you by default, but we often explicitly do it just to make sure. I'm doing a module force purge and then a module load. I like to do that in my batch scripts just because it makes them sort of self-documenting. If I go back later and say, oh, how did I run that model? I can look at the batch script and see exactly what software was loaded. And then at the very end, running an MPI program. MPI bind is a little helper tool that launches the MPI test. Okay. I'm getting the nod from Cecile, so we're almost done. The only commands you need to know for PBS, qsub starts a job, qsub batch script name, qstat says, how is my job doing? So when you do a qsub, you get a job ID. If you want to know if your job is running or queued, you would say qstat and then that job ID, and it tells you the status of it. If you need to delete one, qdel on that job ID should remove it from the system. qcmd is a command that will run something for you, but instead of running it from a login node, it sort of automatically shuffles it off to a batch node. I think you're going to be using that to compile this week, so that'll come up again. Yeah, again, module sets. I think I kind of mentioned just the module save and module restore. If there's a particular environment you always want to be your default, use those commands to make that your default. Yeah. Again, so I think this is my first slide and also my last slide, probably still the most important thing. That's how you get help. And in addition to the ways to get help on this slide, you can come and bug me today also.
Yes, thank you so much. Yeah. Then we have a few minutes for questions. Rory will be in the room, and also each time the slides are uploaded on the tutorial website. And if you are afraid that you didn't remember everything he said, you can find the slide. Okay? A question. Wait, we need the microphone.
So for password, do we need to come to you or to a particular office? I missed that part, sorry.
You should have been given a password already. No?
Okay, then who didn't get a message saying this is your account? Okay. And if you are not an auditor will not get anything. Then there are two kinds of people that are not auditor. Then there are the people who already got an account. That already, if you had already an account on derecho, you will not get a second one. You will use the one that you already have. But we have to make sure that Rory add your name to the special queue we have and also to the account number. Then this is the first thing. If you don't have an account on derecho and you didn't receive an email telling this is your account, you should talk to Elisabeth or to you, to Rory as soon as you can. And then if you have already an account on the derecho, check with Rory that he has added you to the special queue and to the account number. Okay, does it make sense what I just said? Or if you have no clue what I'm talking about, you just...
I think like at the first lab session, so the way things break every year, the first day, there's a bunch of people with password problems. Happens every year. That'll happen again this year.
But it's good that we have already identified that.
Yep. So I think I'll probably maybe wait around for about 10 minutes at that first lab. All the people with password problems come and identify yourselves, and we can all go down to the help desk as a group and be like, hey, help us out.
Okay, then this is important, and I see yes already started a list
And in
of
fact,
people.
I did have one question by Ishrat Dolan, and you are already part of the reservation, so you should be good to go.
Okay, this is good. But yeah, and maybe you have been added already because when you apply, we have CESL look if you have an account, and if you have an account, then they told us that you had an account, and we add you on the queue. But it's not sure that it's better to check because we might have a few falling through the crack. Any more questions for Rory? Okay, then the slides are on the website, and we are going to move to the next talk. And it's good if we have some time after just to fix all the problem. Oof. Okay, thank you. And then for the next presentation, oh, there is still one before we go. Yeah, no, sorry, we don't leave yet. You don't know what you will have to do. Then the next presentation here, this is Kate, and she's a software engineer and scientist, and she is a lot of things. Then she's going to introduce you of what the exercise that you will do today. Then, yeah, this is her talk. Then, yeah.
You guys hear me okay? All right, cool. Yeah, my name is Kate. I'll be here to help with the labs today. And all right. Ooh, now I'm even louder. Okay. I'll try to do this quickly so that you guys have as much time as possible to get in the lab, but I just wanted to give you an overview of what you're going to be trying to do today. It's maybe, a basic level that everybody is already, not everybody, some people have already done. This may be completely new to some people, and that's totally fine. We're used to that. It happens every year. So basically, there's 3 goals for today, and this is both the lab this morning and this afternoon. Your first goal is to finish the prerequisites from the website, which is to get your terminal up, to log into Duratio, to explore the space. And then we want you to be able to check out CESM and understand the code there. And then the third goal is going to be to create and run an experiment with CESM today. So even if you've done all of these before, you should still go through them, especially the create and run experiment, because the labs throughout the week will refer back to the experiment that you guys do today. But also, it's a good idea just to make sure that you're on the same page as everybody else. Cecile wanted me to make sure that we point this out right away. So for wireless access here, you guys should use the UCAR Visitor Wireless on your laptops. If anybody has any issues with that, again, we'll be around to help. If you have EduRoam on there already, you can use that as well. But if you don't have it installed, then don't mess with it yet. We have set the project account as a default. So we have a specific project account for you guys to charge your time to. And we have a specific queue set aside so that you should be able to use the machines faster than everybody else right now. And all of that is set up in this .profile file, which I'm going to explain a little bit more in a slide in a second. But in the lab materials are instructions on how to use those 2 numbers so that you can get everything charged correctly and move through the machine as quick as possible. So for the prerequisites, some of you may have already done this already, but we definitely want to make sure that you already have a terminal. Mac has a terminal program built in, but you may want to install Xports to use the X Windows there, or you can use some of what Rory suggested for X Windows instead. PC has a terminal from the start menu, or you could use the FastX option that Rory was talking about, or some of the other ones there. But basically, you're going to be pulling up your terminal and then log into the Duratio supercomputer with the SSH. And then this is another option. He did the -L for your username, or you could use username @ which is how I've done it before. Once you get in, you will start in your home directory. And one of the first things that you're going to want to do is copy over the .profile file into your home directory. So this is the one that we set up for the tutorial. It has all the modules loaded, everything set up for you already in your workspace so that you don't have to worry about too many things. It includes your project number and, yeah, the software stack and everything. So this information, you can see my little link here, is in the resources under set up your in-car HPC environment. So you should be able to follow the instructions in the lab material previously. But yeah, this is definitely the first step, is to set up your profile. And then once you get on there, you can explore Ratio. And this is just, Rory had this slide too, basically, but you're going to have your Glade quota command shows you your workspaces, your home directory is where we're going to keep everything for this tutorial. You don't have to worry about the work directory. I am wrong, it is not backed up. Thank you, Rory. So just don't worry about work today. Scratch directory is where everything is automatically sent. So when you run your experiment today, all of your data is going to be going to your Scratch directory, and also your build and all of the nameless files and configuration files for your run as they're set up are sent to your run directory in Scratch. And hopefully you'll get a chance to take a look at all of that today. And then the campaign space is sort of the fourth space where we keep all of our long-term data. It's not important for this tutorial, but if you have access, you could take a look today. So like I said, the second goal today is to download CESM. There are instructions for this in the tutorial as well, which I linked to here. But everybody's going to be downloading their own copy of CESM from GitHub. And then once you download it, we'll use manage externals to pull in the code from a lot of other repositories so that you have the whole code base in one place. So this is a good time to talk about Git and GitHub. We use this extensively for CESM because CESM is free open source software that's available to anybody. And this is a public website that we use to distribute that. It's also the place where we organize our issues, track code changes and modifications through pull requests, keep track of all the external repositories as well. So if you guys get a chance and you want to take a look at the CESM GitHub repository, it's a good place to actually look at the code that you're going to be using. So once you download the code, you need to know about basically 4 different spaces that CESM sets up on the machine for you. So your CESM code is in your source root. In this case, it's going to be in your home directory. We're going to put it below the code directory in the home. So the source code is one directory that you kind of leave where it is. You shouldn't need to make any modifications to that for this tutorial. And then the next thing you're going to create is a case. So each case describes an experiment that you're setting up with CESM. It describes the resolution, it describes the number of components that are active or inactive, and which types of components you're running. It describes the forcing files and the types of forcing that you have. And all of that goes into your case directory. So in this case, you're going to have Glade U home username cases and then the case name. And that directory has all of that information in there. And that's where you do most of your interacting with your experiment, where you set it up and you say build and you say submit from there. Once you build and submit, then you're going to create your build, your object root, and your exe root. And those are all done on Scratch. So like I said, the model sets that up automatically for you in the big Scratch space. And you can take a look at that. That's where everything that, as the model runs, it uses those specific files. And then finally, once it's finished running, it actually automatically takes your data and saves it to an archive directory where it reorganizes it in a component space. So you get to see your atmospheric files under Atmo, you see your ocean files under ocean, things like that. So that's all done for you automatically in your archive data directory, which is also on Scratch and set up for you under your username, archive, and then the case name. So you should be able to take a look at all of that today. Does that make sense? Okay. Do you guys have any questions about what I've talked about so far? Nope. Okay, cool. And this is all in the tutorial information as well. You should be able to read it and work through it on your own today, but I'm trying to give you an idea of what you're going to be doing. Each case, this is all in the materials as well, but it's important to note that each case, each experiment that you set up has 3 required arguments. You got to give it a name, you got to give it the resolution that you're looking for, and you got to give it the configuration, which is what we call the comp set. And so that's which components are active and which active components you're using. So I think in the CSM overview today, you already probably talked about that mostly. So for this first exercise and the goal, this is really all you guys have to work through today. It's just these commands. If you can get these commands to work, then you are awesome and you are doing great and ready for the rest of the week. So we're going to make your case directory. We're going to go and find our SEAM directory with the scripts, and we're going to create a new case in that case directory, which is what's here. It's going to be a B1850 case with a 2-degree resolution. So here's the comp set B1850. And then we're going to go into that case directory. We're going to set it up. So the case setup, which is the first step for every CESM experiment. Then we're going to build the executable. And like Rory suggested, in this case, we're going to build it on a compute node instead of on the shared input nodes. So that's why we use the, lost my thing. Yeah.
Yeah, I just want to point that, sorry, here we just changed name and then it didn't get changed at this level. Go to the case directory. Sorry.
Okay.
Okay, let's go back to your slide.
Okay.
Yeah, then, yeah, this thing here, we are going to change it, but it's B1850 basic.
Okay. B1850. I'm sorry, I had the wrong
And
name
then the QCMD command, it's to allow you to run, to compile in the special queue. We think it's the right instruction, but as the special queue was not created last week, we could not test it. But this is, Brian thinks it will work. Okay, then if it doesn't work, be patient. It's the first time we are doing it this way. Then we think it will work, but if it doesn't, we will fix it really quick.
Yes, it's always an experiment. So yeah, you definitely want to run your case.build script on a compute node. Normally, you would just say QCMD and send it off. In this case, you're going to specify a specific queue, so you don't have to wait as long. And then finally, when you submit your run to the batch queue so that it'll run on a compute node that's case.submit, which is the script we use for that. So more information, the CSM bulletin board, like when you finish the tutorial and head home, this is a great place to go whenever you hit issues that you just do not understand. Always search first because probably somebody has had a similar issue and there's a discussion about it there. But if you don't, then you can add one. This is actually an old picture. I just realized that the interface looks slightly different now. But this is the correct URL. And then we also, here's the tutorial materials that you should have linked to in millions of places, hopefully. And if not, then we can plaster it in more places. But this is a really, really useful resource all the way through. And so you guys should read every bit of this that you can. So that's what I got. Now we're going to head off. Cecile will explain what we're doing next.
If there is a quick question, first let's. If there is a quick question, we can ask now. Otherwise, we will move to the library. Then you are going to follow us. And be patient because the first day is always a little bit crazy. We have 3 speakers for the next talk that are going to share the time to speak about parametrization in CAM. Yeah, there's Meg and Christina and Ben. Then I give you the floor. Then you have 30 minutes. Yeah.
Guys hear me okay? Awesome. Okay, welcome back from lunch. So is that better? That's okay, good. Excellent, thank you. So learning outcomes for today, hopefully by the end of this 30 minutes, you'll have an idea of basically what a model parameterization is and why it's necessary. You'll have some familiarity with the main parameterizations that are in the Community Atmospheric Model version 6, CAM 6, and the ability to find more information about any parameterization on your own. So to get started, some of the basics behind what a parameterization actually is. So typically, when I come across questions of what is blank, I go to the AMS glossary, and I wanted to copy the definition here. So the technical definition is that a parameterization is the representation in a dynamic model of physical effects in terms of admittedly oversimplified parameters, rather than realistically requiring such effects to be consequences of the dynamics of the system. Now, if you're anything like me, my brain just isn't quite at this level most hours of the day, so I also want to show you the Wikipedia definition. It's a little bit more easy to understand. A parameterization is a method of replacing processes that are either too small scale or too complex to be physically represented in the model by a simplified process. Okay? So let's try more of a real-world example. So imagine, just for a second, you're in Paris and you're going to the Olympics, but your phone is broken. So you can no longer zoom into a map. So if you only had the map that's here on the left-hand side, there's a lot of detail there. You can see all the streets, there's different rivers, different districts that are labeled. But if you can't zoom, this is ultimately kind of useless, right? What would be more helpful is having a map like on the right-hand side, where it's simplified. So you've taken some of the complex information from a really detailed map and distilled it down into just the basics that you need to know that can help you get around. Essentially, this is kind of the idea behind parameterizations. So a parameterization takes complex, detailed information and turns it into a simplified representation at larger scales. So it doesn't have all that fine-scale detail. The goal then is really to capture the impact of smaller subgrid phenomenon on the larger resolved scale. So if we move away from the Olympics and we think more about atmospheric processes, what kinds of things would an atmospheric model need to parameterize? Well, one thing that's really commonly highlighted is clouds and subgrid scale cloud microphysics. Right, so in this picture you can see, there's 2 different types of clouds here. Something different is happening at the upper levels than is happening at the lower levels. There's little gaps in clouds that are happening. Within the clouds you have different turbulent mechanisms happening. There's coalition happening of rain droplets, ice nuclei, things like that. So all of those things are typically parameterized in a global climate model. One of my favorite examples is when you think about a squall line thunderstorm. We have all this really deep convection, and what happens at the surface is pretty complex. Right, when you have a big thunderstorm happening, you often will form a cold pool with the leading gust front. Those kinds of small-scale features are going to be hard to capture when you're working in a regular resolution of maybe 100 kilometers or so. What goes into choosing parameterizations and what kinds of things do you parameterize? One really important key is how big of an impact is it going to have on the Earth system? So one thing I think about is, do we start with parameterizing the shape of a leaf on a tree? Or do we start with parameterizing saying there's a forest here full of trees? Right, you can imagine having a bigger impact from land use than you can from just the shape of a single leaf. Another thing to consider is computational expense. So ideally, one of the benefits of using parameterizations is that it should be cheaper to run that than representing the entire really complicated process in a lot of detail. So parameterizations help us there. And there's also process uncertainty. So sometimes the things that happen at really fine scales, we just don't understand in full detail what leads to what. And so when we're uncertain of what's happening at a very small process level scale, we can parameterize the larger scale effects of whatever that smaller scale process is. So hopefully you have a broad understanding of what a parameterization is and why we need it. A parameterization is a way to represent unresolved and maybe uncertain subgrid processes for the impact on the resolved scale. Now, often they stem from physics, things like conservation principles. They can also come from observationally derived constraints. So just something to note there. And with that, I'd like to hand it over to Ben to talk about some of the main parameterizations in CAM6.
Hello, can you hear me? Is it working? Okay. I'm Ben. I'm also one of the helpers for the tutorial, so you might see me in the library. Yeah, I'm going to talk about a couple of the parameterizations in CAM. The first two here, namely convection and radiation. And let me just say at the outset, these are complicated codes that we're talking about, so there's a lot of detail that just can't be captured in a short little discussion like this. So I'm going to give you kind of a high-level overview of a couple of these different pieces of code in CAM. So radiation, so Meg was talking about how you can have like a process that's just too small to really be captured at the coarse grid resolution of like a standard model, like 100 kilometers. And of course, radiation is fundamentally a microscopic process where you have photons interacting with different kinds of molecules in the atmosphere. We can't hope to even come close to modeling something that detailed. But, and this figure here gives you a sense of all the complicated things that are going on in the atmosphere. There's two main sources of radiation that go into the atmosphere. One is solar radiation or shortwave radiation, which comes in from the sun, of course. And then there's infrared or long-wave radiation, which is heading back up from the surface. But they don't just, these photons, they don't just pass through the atmosphere. They can interact with things in the atmosphere in all sorts of ways. They can be reflected off of various things, clouds or ice or water at the surface. They can be absorbed by various gases. Shortwave radiation is absorbed by ozone. Long-wave radiation, as we know, is absorbed by greenhouse gases and gets trapped in the atmosphere. So there's lots of complicated things going on here. The model that CAM uses to try to simulate this is the Rapid Radiative Transfer Model, or RRTM, and its various descendants. In CAM6, we have RRTMG, and there's another one in the works called RRTMGP. So it's kind of evolved and improved over time. But what this code ultimately does is tries to give us things like the radiative flux at the surface, the radiative heating and cooling rates at each model level, depending on what we think is going on in the particular grid box where the calculation is taking place. And right, so this will take into account radiatively active gases like water vapor and carbon dioxide. So if you have questions about the details of this model, we have good people here who can help us answer those questions. Convection in CAM is handled actually by two different models, depending on which kind of convection we're talking about. So there's shallow and deep convection. Shallow convection both extends less high into the atmosphere. It's sort of contained within the atmospheric boundary layer up to 1 kilometer or so. And it's also sort of horizontally smaller scales, so maybe hundreds of meters up to, say, the order of kilometers. And deep convection, can go much deeper throughout the troposphere or even into the lower stratosphere, I think. And you can have much larger plumes that can be, maybe up to tens of kilometers across. Now, even though these structures are much larger, say, than the like photons and molecules we were talking about before, notice they're still smaller than the grid resolution of a typical model, which would be 100 kilometers or so. So we still have to parameterize these. And in CAM, we have this model called CLUB to handle shallow convection, and then a Zhang-McFarland scheme, or as we call it, ZM, to handle deep convection. So I'll just go over a little bit about those, and then I'll be done. So CLUB is actually the model that I work on, so this is the thing that I know best. CLUB is really fundamentally a turbulence model, but because the boundary layer of the atmosphere is where all the turbulence is, basically, it also incorporates shallow convection and shallow cumulus clouds and stratocumulus clouds. And basically what it is, it's a system of coupled equations, like the Navier. Well, these are kind of tough to derive, but they come ultimately from the Navier-Stokes equation, conservation equations, things like that. And I've given a couple of examples here on the right. So at the top, you just have the equation for the grid mean total water, R sub T. But in order to calculate that, notice there's a term that has this this blue term, W prime RT prime. And club contains a prognostic equation for that. That's the lower equation. And then notice that equation has this green term in it, W prime squared RT prime. So, and this is kind of how turbulence theory works. You keep having these higher and higher order terms in your equations, so you have to stop somewhere and close these terms. And club uses two different methods of closing them. The green terms are closed with a subgrid probability distribution function, or PDF, which in club's case, it assumes that the PDF has a certain kind of shape, namely it's a double Gaussian. Don't need to go into the details too much, but, oh, and I guess there's some overlap there, sorry. We can integrate over that subgrid PDF to close terms like W prime squared RT prime, because this PDF is actually a distribution function for velocity, temperature, and moisture. So that's the velocity W and then the moisture RT. And then there are other terms like these PR1, PR2, PR3 terms. Those are ultimately coming from the pressure gradient term in the Navier-Stokes equation. We can close them using sort of standard methods in the turbulence literature. Now, this is just intended to give you a sense of what club's PDF is like. Now, because it's a PDF for 3 different variables, we can't visualize it on a 2-dimensional, screen. So, but you can visualize the marginals of the PDF, which means that you integrate out one of the variables. So the interesting thing here is, well, what the PDF is intended to do is to give you the probability of finding a certain kind of situation within a model grid cell. So the central panel of the plot may be the most enlightening here. That blue line that you see is the saturation line. So anything on the right of that is considered saturated, and anything on the right is not. So looking at this, I would guess that this grid box is actually almost certainly not cloudy, because the peaks of the PDF are on the unsaturated side, if that makes sense. So that's just to give you a sense of that. And then finally, deep convection is handled by the Zhang-McFarland scheme. This goes back to a 1995 paper, but the code has been improved and evolved over time. And we have documentation linked here that you can look at if you want to learn more about it. It triggers based on CAPE, convective available potential energy. So the stronger the CAPE, the stronger the deep convection. It uses a mass flux approach to calculate the air motion within the plumes that it models. It has parameters that control entrainment and detrainment. That's when a plume essentially either draws air into it, entrainment, or sort of expels air, which would be detrainment. And yeah, ultimately what it gives us is the convective heating and moistening at each level of the model. So those are some of the parameterization schemes. I'm actually going to hand it back to Meg, because she's going to talk about a possible unification of club with deep convection in the future. And she works directly on this project, so I'm going to give it to her.
Awesome. Thanks, Ben. So I just wanted to pop back in for a minute and give you an idea of what lies ahead for CAM, in particular with regards to convection. So as you can imagine, having 2 different schemes deal with shallow and deep convection is a little messy, right? Where exactly is the line between shallow and deep? A cloud in reality is not making that distinction, it's just growing. So as we move forward, what we're looking at is, can we actually unify those 2 schemes in one? So there's been work led a lot by Adam Harrington and Michael White, looking at how we can add on to club. And the idea is club MF. MF stands for mass flux, and club is just what you heard about before. So we keep club, and club handles kind of the shallow convection side of things. So club's totally fine doing what it's doing. But the addition here is explicit mass flux plumes. So these are organized updraft plumes. You basically initialize an ensemble of them. So say you have 10 updraft plumes. Each of those 10 updraft plumes is actually going to go through the calculations of how much is it growing, how is it detraining, where is it going to terminate. And then all of that information is averaged back together and used in CAM. So to give you an idea of kind of why this is important, these are, again, kind of the PDFs that Ben was showing before, looking at the distribution of theta L, temperature on the bottom, and moisture on the y-axis. in LES, which is in gray. So LES is large eddy simulations. These are really high resolution model simulations, much higher than we run CAM at. And because it's difficult to get observations of this, we kind of use LES as a proxy for observations. So consider the gray lines is what we should be seeing, and then the black lines are what club alone will give us. So we're kind of in the right area in our club representation, but we're missing a lot of the tails, right? These extremes are just not something that club can actually capture very well. The beauty of MF is shown with these black dots here. So these are these individual updraft plumes. As you can see, they tend to be stronger, so they have stronger moisture and temperature anomalies, and they capture better this full distribution that we see in LES. So this is something under development right now, but I think it's a really exciting move as we think about the future of parameterization. So just to give you a taste of what's to come. And with that, I'm going to hand it over to Christina.
Thanks, Meg. Okay, so we're going to zoom in a little bit further into an even smaller scale process, which is cloud microphysics. Raise your hand if you guys have studied cloud microphysics. I'm kind of curious. Raise it high because you know it's the coolest topic, okay? All right. Okay, so in CAM, we use the parameterization of unified microphysics across scaled. This is formerly known more commonly as the Morrison-Gettelman scheme, but we've changed the name because more people are contributing to its development. So this used to be called MG, MG2, MG3. Now it's called PUMAS, okay? PUMAS is a two-moment microphysics scheme, which means it can predict both number and mass. We represent four main classes of hydrometeors for clouds: cloud droplets, ice crystals, rain, and snow, and of course, water vapor. And I wanted to give something that I particularly spend a lot of time on is thinking about how to constrain the cloud microphysics scheme. So here's just an example of some observations from cloud probes from my aircraft. Compared against the CAM predicted microphysics. So you can see these beautiful colored full gamma distributions. These are from the model. And then in the black are the measurements from these different cloud probes. So a little bit more variability. And these are looking at the number concentrations of each of these hydrometeors or different sizes from Southern Ocean clouds, so a mixed phase cloud. But what you can see is doing these types of comparisons, we can learn a little bit about the model. And in this particular case, we see that there's these more cloud droplets here, maybe more rain predicted in the model than in the observations. But this is the type of information we can get from the model. So very, I would say, sophisticated microphysics scheme compared to what there was in, for example, CAM4 and CAM5. A little bit more, I'm going to go into a deep dive of all the microphysical processes, so hopefully you guys are ready. But this is just to give you an idea of how complicated these schemes can be, okay? So here I'm going to just walk through a warm phase cloud. So we have water vapor that's really driven by the dynamics we already just heard about. Cloud droplet activation requires some information from the aerosol scheme, which I'll talk very briefly about, to get our cloud condensation nuclei. And that, of course, controls the cloud droplet number and mass. And then these cloud droplets can, of course, evaporate. We also have two processes in the model named autoconversion, which is where droplets grow large enough to be transitioned to a large droplet or rain droplet category. And then accretion, which is where cloud droplets, as they get bigger, they can collect other cloud droplets and grow that way. So these two processes allow for cloud droplets to transition to the rain category. And then rain can also evaporate. And then, of course, the sedimentation of both of these warm cloud hydrometeor types. Things get more fun when you go to mixed phase. So now aerosol can serve as ice nucleating particles through this heterogeneous ice nucleation process. We have ice crystals that can form that way. Also through homogeneous freezing. We also represent the sublimation of those ice crystals. And then similar to rain, we have an autoconversion process of those ice crystals growing to snow sizes, and then the accretion of ice by snow, and then of course snow sublimating. We also represent the freezing of rain, which can contribute to both snow and ice. And then there's a highly uncertain part of cloud physics related to ice multiplication or secondary ice production. And this is represented using riming and then the shattering of those large ice crystals. So that's all represented in PUMAS. So you can imagine there's quite a lot to read in the Fortran code. So if you have any questions about this, I'm definitely going to be your person to ask. And then also you can turn on in the new Puma scheme, we also now represent grapple, which is kind of a mix where snow can collect supercooled liquid and it grows into these large hail and grapple particles. So now we're also representing this process. That's new. Okay, so now moving on to aerosol. This is the modal aerosol scheme. This is what we're currently using in CAM. If you are familiar with aerosol, you know that they can have a bunch of different compositions, a bunch of different sizes, and different properties. And in CAM, this is pretty much simplified to these 6 categories. So we have black carbon, dust, sea salt, particulate organic matter, which is mainly emitted with biomass burning, sulfate aerosol, and then secondary organic aerosol, which comes from the emission of gaseous precursors that then transition to aerosol particles. The scheme is using a modal scheme, like I said, and this is demonstrated here, where we have these, again, complete log normal size distributions, and we can do similar things to what I showed earlier, comparing those to observations, but this is an example over the Southern Ocean where you can see the sea salt particles and the sulfate particles dominate that aerosol population. So that's just, I don't know, a cool example in my mind. But okay, so this is really powerful because it allows us to do interesting experiments in CAM. I just want to give you an example of a study by John Fasulo, who's here at NCAR, who looked at this extreme wildfire event in Australia in the 2019-2020 wildfire season, where they were able to use the CAM model to simulate all this black carbon and biomass burning emissions, and then looked at the large-scale impacts of that aerosol flux. So that's why it's important to have these types of aerosol in the model, and that's our MAM scheme. Okay, so now from here, hopefully you have some familiarity, at least some buzzwords that can start with some nice literature search, but we wanted to just give you an overview of all these different parameterizations. So finally, we wanted to kind of share that, well, you know, these parameterizations are very complicated. It's impossible for us to cover everything in a 30-minute talk. And really, you probably won't need a deep dive into all of them. It would just be like one module that you would need a deep dive in, right? And so sometimes it's helpful to just figure out, okay, well, how do I learn more information about a given parameterization? So we thought we have one slide, and I think they're going to have these slides, so you guys will be able to see this. So of course, there's the GitHub CAM6 documentation. We also have a lot more information, like technical documents for Club that Ben pointed out here. And then there's some main parameterization papers, which are a really good starting point for a lot of these parameterizations. We've tried to find the most recent papers that describe the different schemes. And then something that we were kind of joking about is probably one of the more useful tools is what we're calling a scavenger hunt in the terminal or your command line, which is using this tool grep, which when I started as an observationalist, similar to you guys, having never really worked in a terminal before, I didn't know what grep was. So I wanted to share this as a very helpful tool where you can basically search through your entire directory and find keywords. So say you want to look for what impacts cloud liquid. This is the example here. Then you would type out this in your command, and it would search all of the modules for this keyword, and then you can kind of deep dive and see what is kind of touching that variable, if that makes sense. Okay, and so then from here, we're going to take questions. We have plenty of time, and we can also talk in more detail if you guys have more specific questions for your research projects or whatever. So thank you. Oh, hang on.
Okay. Thanks, everyone. I'm just curious what goes into, so on that last slide, there was dynamic versus, or dynamical versus whatever the opposite of dynamical is. I'm missing the word. What goes into the choice as to whether or not to make a parameterization scheme dynamical or pre-described?
Who wants to answer that? Anybody?
I think if you go back like 2 slides, Yeah, that
Oh.
one. Yeah, so sorry, dynamic emissions.
Okay, yeah.
Oh,
sorry.
never mind. I get
so,
it.
yeah,
see.
no, this is something I should have mentioned, but I didn't. So thanks for the question. So seesaw and dust are both what I'm calling dynamic emissions, meaning that they are dependent on the model wind speed or land surface conditions, whereas like biomass burning emissions and like pollution-related emissions, those are all based on emission inventories, which are provided in the comp set and the forcing files that when you set up your model. Yeah,
got it.
So
Thank
that's
you.
the difference. Yeah. But at the same time, all aerosol go through the same physics of like cloud activation, scavenging, all that stuff. They're all treated the same that way, just their emissions are different. Yeah.
Nice talk. So I have a question about this new PUMA's cloud microphysics scheme. So in this, do you represent like secondary ice production processes as well in the
We
new
do.
scheme? Okay.
We have one mechanism. So secondary ice production is a very highly uncertain process, and there's like 8 mechanisms that are currently recognized, but only one that's been parameterized and put into most GCMs, and that's the Hallett-Mossett process. So we have that, which is the rimed particles that then shatter, but we don't have like ice-ice collision, droplet shattering. Those things are not currently in the model, but they're research activities.
Mm-hmm.
Yeah.
Okay. Thank you.
Yeah.
Question?
I think you might have answered this with the first question, but I want to make sure that I understand it. So my question was, are there parameterizations that happen in between model components, like, or are they all within one model component? And maybe the answer to that question is that dynamical parameterizations are when you are relying on other components. Is that correct?
Yeah, I mean, so this is actually my like happiest thing ever is parameterizing interactions between components. It's somewhat, I don't want to say totally new, but typically it's not something that gets a lot of attention. So there are parameterizations of, say, fluxes from the ocean, just taking into account atmospheric wind speed, humidity, things like that. And so that parameterization will take the fluxes from the ocean and send them to the atmosphere. The hard part is it's really, really simplified. So right now we're communicating on like a grid scale level between, different components. You can imagine, say, in the land, you have 2 different surface types, maybe an urban area and a lake area. Ideally, you'd want the atmosphere to know that those are the surface types under it because there's going to be weird things happening over each surface. So we don't quite have that yet, but it is something that a lot of us are working on, or at least a few of us are working on. Excellent question. Yeah, not entirely, but we're working on it.
Similarly to the land use case, is anyone working on like ocean fronts or really sharp like contrasts in temperature within a single grid cell?
In the ocean model?
Or like you expect it to be in a certain place in the ocean model, and so you tell the atmosphere that there should be a front there, that there's a boundary current, that sort of thing.
Yeah, I don't know of that. If anyone else does.
I'm not aware, but that doesn't mean it's not happening.
Okay.
So
Right, yeah.
We're atmosphere people. So. I'm kidding.
Good questions.
Thanks, that was really enjoyable. I have a question about context to other models. Could you maybe have a few sentences on how do other models, especially for, let's say, smallest time and spatial scales, handle this? And where do you decide completely different than those schemes?
I can speak to microphysics if you'd like, which is, a lot of, actually, SUCC is here, who does direct numerical simulations and is able to resolve like every particle, for example, in a cloud. And so you're going to have a lot more of a physically based model, right, entirely. Whereas here, because we're on a 100-kilometer grid scale, we have to make these simplifications. So in the microphysics world, there's quite a huge diversity and value in using what we call model hierarchies, where we look at small scale and higher temporal resolution and then try to bridge those over to the large scale, which is not easy. And it's also expensive. So anyways, I'll just say that there's a whole realm of different schemes. In terms of other GCMs, I think that PUMA's is a pretty advanced one in that it's, in terms of countering the expense and the physics. But there are more that are more sophisticated that they'll do perhaps bin microphysics, where instead of having these modes, they have like a more sectional scheme where they're trying to resolve different bins of sizes, but that's more expensive. Now you have, 6, 7 species per hydrometeor to chase around. So anyway, it's just kind of a play of cost and physics. Yeah.
And with regard to convection, if you, as you increase the resolution of your model, you can actually turn off those convective schemes. So Zhang McFarlane, for example, if you were running a kilometer scale model, you could probably just turn it off. Club as well. Like if sometimes I'll run LES tests, large eddy simulation, and if you're running at on a grid of 100 meters or something, you can just turn Club off and let the LES handle the turbulence. So yeah, it kind of depends on the resolution you're using.
Thanks for the introduction. I'm just curious about how you get the cloud properties from like the cloud base height, cloud type, and cloud cover from the model. Like that included in the some like schemes, or like you have different ways to get it, and also specifically how you get the like specific output, like the cloud fraction, that's actually incorporates like the vertical distribution of the clouds.
Okay, are you trying to compare with observations?
No, I mean just how
in general?
how the model get the output, like how the model calculate that.
Okay, yeah. So it's a interaction between actually 3 different schemes: MAM, the aerosol scheme, Club or ZM, and then the microphysics. And so all of those work together to predict the cloud formation process, and then things like the cloud evolution and lifetime, and all the evaporation, sedimentation, like all these things that could influence that cloud fraction. And then so every time step is predicting these cloud properties. So you can imagine there's quite a few output variables. And then the output, you can get global fields, like top of atmosphere fields, where it will give you that like column cloud fraction or the column cloud amount. But then you can also have it resolved all the way to the vertical resolution, where you can find where exactly those clouds are within the column. And that's where you could calculate your own cloud boundaries and things like that. But the model does all of that type of math and physics through the combination of MAM, Club, and Pumas. Yeah. Yeah, cool question. Thanks.
Hi. So my question is related to the previous one, where Ben mentioned that if you are running LES mode, you can turn off the convection. So in CSM, is there a possibility to run like very high resolution and still get a good representation of the microphysics of physics? Or is there like a limitation that we cannot set a resolution lower than which the assumption couldn't hold?
Yeah, that's a good question. Definitely, yes, you can run CESM in much higher resolution configurations, yeah. The standard configuration is like a 1-degree model, basically, I think, where you're running at basically 100-kilometer resolution. But the guy I work for, he's running 8th degree simulations, which are much, much more expensive, and he can only run them for like 6 months at a time and stuff, so it's a lot more expensive to do that. I can't comment actually on the quality of those simulations. I think that's something we're currently investigating. I'm actually helping him to kind of study, what we're seeing in those. I don't know if you guys have comments on that, but
I haven't looked at the high resolution runs, so I don't know. Yeah.
No, I haven't either. In
Peter,
land, it's
Peter
harder.
maybe has a
Yeah.
comment in the back.
Sorry, we need to pass the mic. We've been running a version of CAM7 physics at 3 kilometers. And the people who are running that were really interested in squall lines, and they were able to get a squall line that was like competitive with the WRF model with a tweak to the microphysics. And I don't recall what it was, but it's just a anecdotal example of that it can work in that application. But as I discussed in my talk, certain assumptions start breaking down at those scales. So there's definitely a lot more work to be done on that end.
More question? Yeah.
In the club scheme, you mentioned that there were higher order terms that were closed not using the joint PDFs. Could you talk a little bit about what you're doing there?
Yeah, so if you look at the Navier-Stokes equation, there's a dP, well, basically it's a gradient of the pressure. This is a pressure gradient term. If you look at these higher order equations, that pressure term keeps showing up. And there's turbulence, I mean, like there's theory going back decades in the literature for how to handle these pressure terms. And Club uses some of the standard formulations that go back to the late 70s and early 80s. There are open questions in this area. I mean, I don't, you know, there are terms that, for example, people decided decades ago that that term was probably going to be small, so they left it out of the model. So that's one of the things I've actually worked on, like as a postdoc, and now that I'm here, is the possibility of incorporating some of these missing pressure terms and coming up with new parameterizations for them. So I mean, I'd say the work is kind of ongoing, but there are some that are like, there are some pressure terms that are pretty well understood, at least in terms of how to try to model them. I don't know I mean, if you're interested in the mathematical details of it, you know, you could maybe email me or something and I can send you papers that you could look at, but it's maybe a little bit too complicated to describe the equations. Yeah.
Any more question? Otherwise, can I ask you to stick a little bit? We are going to have a break. If you can stick a little bit, then if people are shy to ask a question in front of everybody, but then yeah, they will stick a little bit. We are going to break. There will be no snack now. The snack will be coming later when we go to the library, and it will be in the diamond room. Then yeah, don't look for snack. There is none. Okay.
That's up pretty well.
Okay, the next talk, it's Clara Desser. She's going to give a talk on climate variability. It's an example of a scientist that does, you don't develop the model itself, but she uses a lot of the result, and it's really cool, the kind of thing that we can do.
Okay, thank you very much. Such a pleasure to meet all of you, and it feels so good to know we have a room full of the next generation of climate scientists and people who are interested in just the science in general, but also using the model. And I'm in this really privileged position to be able to work with people who run the model. I actually don't personally know how to do it. So just honest admission here. But we get to do very interesting science, and we do it with each other. We really think creatively about ideas. So today I want to talk about a recent project that is just in progress and very much inspired by Steve Yeager's work. And thank you very much to Adam Phillips, Nan Rosenblum, and so many others who have really made essential contributions here. So as you all know, we have had an El Nino event this past winter. It's now transitioning into a La Nina. And we were interested in what the climate impacts of this El Nino are and how we can understand them and attribute them to various factors. So Steve Yeager and a whole bunch of colleagues here have pioneered this use of the CESM2 to do it for initialized predictions over time horizons of seasonal to multiple years. It's been an incredible success. It's probably one of the best coupled model prediction systems there are out there. So one of the successes of the model is its ability to predict El Nino and La Nina events. And they've run these hindcasts of the predictions using different start dates all the way back to 1970. And here we're looking at the sea surface temperature anomalies in this eastern equatorial Pacific, Nino 3-4, for boreal winter. And these are the hindcast predictions of the model from November 1st, and these are the average values for each December through February season. I don't need to report what that correlation coefficient is. Obviously, the model is incredibly skillful at this 1 month lead time, at least for the DJF. So the model is skillful. And here was the forecast done on 1st of November last year, predicting like the fourth strongest El Nino in this last 50-year record. It turned out that this forecast verified to within 1/10 of a degree. So again, very successful forecast. So one thing that we have to pay attention to is that this El Nino occurred within a background changing climate. So here we're looking at a map of the observed sea surface temperature trends starting in 1979. This ends in 2020. This particular figure doesn't look very different if you update it to the current winter. So you can see that you have a lot of warming over many regions of the globe, as expected from anthropogenic influences. But then you can see the eastern tropical Pacific, especially just south of the equator, actually had a slight cooling over the last 40 years, and the Southern Ocean as well. So this El Nino is happening in a world that has a background climate change. So what I was interested in, my group was interested in, are what are the climate impacts over, especially North America, from this El Nino event, and how are they modified by this background climate change? So that's where we step in and use the model as our, kind of sandbox to really play with it and try to tease out different factors to try to address this question. So I will now explain what we did to try to answer this question. So our experimental design, we take in the gray box there, that is the fully coupled model. That's what you're learning about, and all of its components, ocean atmosphere, land, sea ice, etc. And we take the predicted sea surface temperature field from those initialized predictions on the 1st of November of last year. And then we take them as departures from the model's climatology. And to that, we add the observed background SST change that you just saw the map of. And then we have to put these anomalies on top of some climatology, and we use the observed, the real data climatology. So we're just using the predictions for the anomalous DJF season, and then we're putting it on top of background climate change that's observed and the mean state that's been observed. And then we prescribe these the forecasted SSTs to the component atmosphere land model. And I think you've just been learning about that. So that model, you need to prescribe something at the lower boundary. These are the SST conditions that we prescribe at the lower boundary. And then we also prescribe the radiative forcings, i.e. the greenhouse gas concentrations, ozone, et cetera, volcanoes that occurred in this past winter. Okay, so that's the design. And we run 50 members of this experiment. Why do we do that? Why not just one? Because each experiment has the same lower boundary condition, the SSTs, and the same radiative forcing. But the reason why you need to run a lot of members is that you have a lot of internal variability within the atmosphere. And one member can give you one rendition of, jet stream variability, and another run can give you a different rendition. So if you want to really understand the response to the conditions, the sea surface temperature conditions, you need to run a lot of members. So that's a short answer on that. So then we wanted to address, as I said, the role of background climate change. So we do what we call a counterfactual experiment. It's not what really happened, but it's what would have happened if we hadn't had that background climate change map. So that SST map I showed you of the long-term trends, we remove those trends from the data, and then we run another 50-member ensemble. So this has the predicted SST anomalies, including El Nino, for this past winter, but it does not contain the background SST trend. So that's our counterfactual, so we can then address what is the role of those background trends. And then we need some kind of control, right? You can't evaluate your experiment. You need some kind of control experiment. So we run two different controls of this atmosphere land model. And control experiments in this context means that there are no anomalous sea surface temperature conditions. It's just the SST field is just the observed mean state climatology that varies over the seasonal cycle. And we ran two different controls. The only difference is the radiative forcing condition. So the one in blue there is the current greenhouse gas, et cetera, levels of radiative forcing. And the one in green is what the radiative forcing was in this 1979 world. So it's very fun to play with the model and do these kinds of experiments, because then you can start to answer all these questions. So if we compare these two experiments, we'll get the impact of the predicted El Nino SSTs plus the impact of the background climate change. If we compare these two experiments at the top, we can then isolate the effect of the observed SST trend and the change in the radiative forcing. And then finally, if we compare the two control experiments, we're isolating the impact of just the radiative forcing in the absence of any change in the lower boundary condition. So that's how we've designed this experiment, or set of experiments. And now I'll just show you some of the results and then open it up for some discussion. Okay, so I'm obviously going to be filling in this slide here, but just going step by step. So this is all going to be for boreal winter, 23-24, this past winter. And these are the SST anomalies that are used for the experiment. So it contains the predicted El Nino anomalies plus the observed background SST trends. So that's what the atmosphere land model is seeing for each one of these ensemble members. So now I'll show you the precipitation response, and then we'll look at the atmospheric circulation. Oh, and circled here, that's the El Nino, but that El Nino is occurring within this background of some background climate change. So here's the precipitation response averaged across all 50 members of the experiment minus the appropriate control experiment. And where you see the black dots, that means that the precipitation response is not significant relative to the variability within the control run. But everything that's not stippled is, a statistically significant signal. So as expected, we see enhanced precipitation in the tropical or the equatorial Pacific, and then some drying on either side of this rain band. And that's a very typical response. We were not surprised to see that. And now here is the atmospheric sea level pressure response. And here, I was actually thought we had done something wrong with the experiment, because this pattern, I've circled the area that we were most interested in, the North Pacific, and that is a pattern that, to my eye, from a lot of experience looking at El Nino and the model, that was not the canonical response that I was expecting. I was expecting just to see a low pressure response that fills the entire North Pacific. So what's going on here, and that's obviously why we did these additional experiments. So now we're going to look at just the response to the El Nino. So this is the set of experiments where we took out the background climate change. So this is, I don't know if it's your grandmother's El Nino or if it's your parents' El Nino, but it's El Nino that it would have, if you had, if it had occurred in 1979, that's what, this El Nino would have looked like. So that's the prescribed SSTs predicted from the model without the background climate change. So now we look at the precipitation response and the sea level pressure response, and I'll just jump right to the sea level pressure. This is what I was expecting. This is what, I studied El Nino for my PhD around 1979, a little later. And that's what El Nino events are very typically show, that are driven, by anomalous deep convection in the tropical Pacific that then excites atmospheric Rossby waves and leads to this canonical deepening of the Aleutian low. So obviously, there's something going on with background climate change. So now we'll look at that. And this is, again, the prescribed SSTs. This is that same SST trend map that I showed you from observations. That's just a reminder what it looks like. And now here are the responses to that SST pattern. And this is the precipitation response. And right away, you can see that that tropical Pacific, it's very much kind of opposite to the counterfactual El Nino, the El Nino that we would have seen if we had lived back in 1979. And then, lo and behold, that background climate change is actually, that's what's inducing a strong ridge over the North Pacific, has a lot of cancellation with the El Nino effect. And then in the end, you get that top map on the upper right, which was a surprise, but it's not a surprise when we take it apart in this way. So, and then I can speak more about the North Atlantic response, but I don't really have time to go into it right now. And then the other thing I don't really have time to go into, but from the set of experiments we've done, we can actually take apart this bottom set of panels and take apart what is the role of the SST trend and what is the role of just having a different radiative forcing, different level of greenhouse gases. So we've done that. Happy to answer questions if somebody asks. So I'd like to just end up, maybe in the last few minutes here, with a closer look at precipitation impacts over North America. We've also looked at air temperature, but I'll just confine myself to the precipitation. So I'll show you the same kind of set of results, but now we're going to focus in on North America. So these are maps of the DJF 23-24 precipitation response. And again, the stippling where you see dots, you cannot find any significant response relative to the control run. So the top map is, the total impact of the predicted El Nino plus background climate change. And the middle map is this counterfactual, your grandmother's El Nino, and then the bottom is the effect of background climate change. So I'll just walk us through a few regions here. It's very interesting to do this decomposition. So up in Alaska, the enhanced rain or precipitation predicted for Alaska, actually that's mainly a signal from the background climate change. It's really just coastal Alaska that has a response to the El Nino. And then we can look, move down here to British Columbia and the Pacific Northwest. And here you can see the dominant impact comes from El Nino with a slight reinforcement of the drying from background climate change. And then we can look over in the eastern part of the US, the sort of north-south dipole pattern in the precipitation response. And that is mainly coming from El Nino and a little bit of counteracting behavior from background climate change. And then finally, Southern California, which of course broke a lot of records for rainfall this past winter. And in fact, it was sort of counterintuitive, but according to these results, so El Nino obviously has a big impact on California precipitation, but background climate change is actually working in the opposite direction. And if there had been no El Nino, one might have expected actually anomalous drought in that region. So it's really important to look at these results from the point of view of probabilities. These are 50-member ensemble means. So we have averaged out internal atmospheric variability. The real world hasn't averaged out internal atmospheric variability. It is, one of many possible scenarios. So NOAA does a very nice thing called their probability forecast, which is making maps of what the chances are of falling into the different terciles of distribution or the control distribution in our case, or the real world's distribution of data. So I'm going to show you now these precipitation maps, but in terms of the probability of having the precipitation either in the middle tercile in the gray, the lower tercile drought in the orange and brown, and then the upper tercile in the blue. So even for Southern California, which is definitely a direct hotbed or response to El Nino, even that for this counterfactual El Nino, the maximum probability to be in that upper tercile is maybe 60 to 70%. So it's not a sure thing. The real world gave us a lot of rainfall that winter, but But according to these model results, that didn't have to be the case. Certainly there are higher chances to be in that upper tercile, but it's not 100%. And then we can do these same probability forecast maps for these other cases. And you can see in line with the upper map on the upper left that the chances for California, for example, of having rainfall, anomalous rainfall in the upper tercile is diminished when you include background climate change. And you can see that the chances of, having background climate change make an impact is sort of roughly a 50% probability effect. So I'm going to leave it there, and I'm just going to give you a one-line summary of the theme of this work. And there's so many angles to look at, but I've just shown you a little bit here. But basically, the El Niños and La Niña events that are now unfolding in nature. We're expecting a La Niña this coming autumn and winter. They are not going to be sort of the canonical El Niños that, their impacts will not necessarily be what we would have expected based on historical data, because these large-scale background climate change, whether that's purely anthropogenically caused or part of it is actually internal variability, I think some of both, that's now going to be making ever-increasing impact. So we have to think about El Niño, La Niña impacts in the light of this background climate change. So thank you very much. Happy to get questions.
Okay, question. Oh, yeah.
Hi. Thanks. That was fascinating. I have two short questions. The first one, sorry if you mentioned this already, but why did you pick the 1979 El Nino as the base case?
Well, it wasn't the 1979 El Nino. I know it's a little confusing. There has been a lot of literature in the past few years about 1979 is the era of satellite-based data. We have, don't have to worry about instrumental, discontinuities or errors. So a lot of people now are starting to look, when they look at long-term trends, they sort of start in 79. I mean, you don't have to. You could have gone way back farther. So a lot of the community has been discussing why has the eastern tropical Pacific been cooling, even though El Nino and La Nina events are still occurring. So it was only for that reason to put it into the context of this trend since 1979. There's nothing magic about 79. And we're not looking at El Nino in 79. Actually, there was no El Nino in 1979. But we're just saying if today's El Nino had happened in the world of 1979 with lower greenhouse gas concentrations and without that large-scale pattern of trends, what would its impacts have been?
Okay, awesome.
Yeah.
And then my next question is, what do you think is the potential for this research related to like forecasting? Because I know this is a hindcast, but do you think this could be useful for understanding future El Nino before it actually happens?
Well, this is a forecast. So the predictions were made on the 1st of November of last year, and we ran all of these simulations before December 1st or before December 15th by the time we got them done. So all of what I've shown you is actually before the event unfolded. So it was a true forecast. I can now, we followed up to compare what the real world actually gave us, but this was a true forecast. So it is a demonstration of, the utility of this kind of approach. The hindcast that I showed you at the beginning, that's just to show that the model has skill, right, when looking back, even though it's doing the forecast.
Did it forecast well? Like when you checked back?
Yes.
Cool. Okay.
Yes. Yes.
Hi. So maybe I missed some detail when you present the only background climate change, did you only consider the SST impact, or did you also consider the land impact from the climate change?
It has, if you are referring to land use, land cover change, we do have, that is part of the background climate change. Yeah.
Okay, and also the temperature change, or?
No, no, we only considered the ocean temperatures as far as I
So that's why we see an insignificant impact in inland of North America. Is that because we didn't consider the background climate change over land?
Well, the model is computing, right, the land temperature response to the sea surface temperature conditions.
Okay.
So if they would favor drying, for example, then the land is responding to that.
Okay.
Yeah.
Okay. Thank you.
And the isolated sea surface temperatures you have there coming from climate change, how do you know, how did you get that? And how do you know that it's coming solely from climate change and not like decadal variations?
We don't. And I've used this term just very, very loosely. It's background climate trends. So we just took the observed trends and we're not attributing them. And I absolutely think that part of the pattern of the SST trends that I showed you in the real world, I think part of that is certainly human caused, and part maybe these decadal, multi-decadal modes of variability. Thank you. Yeah.
Hi, nice presentation. I was wondering if you had the chance to see what happens in the North Atlantic in terms of the NAO, the North Atlantic Oscillation.
Yeah, it's very interesting, actually, and I'll just back it up to here. So the North Atlantic's a little on the side of the map, but you can see where I've circled things. So actually, the upper right, it gave quite a strong negative NAO response. And that is coming, actually, it's sort of partly canceled, partly coming from the SST and partly from the background climate trends, although their patterns are slightly different. I haven't looked into it too much more at this point, but there is very absolutely an NAO impact. Yeah.
Thanks.
Yeah, there were one more, and I think we would, yeah. I will ask you to talk after because we are going to run out of time.
Yes, so I was just wondering, as far as have you utilized this for projections? You know, because as you said, shows that like background climate change, especially in like the California and the Western United States, has a tendency to be getting drier, and we're going into a La Nina, which also like could exacerbate that. Have you done projections to see what this coming winter
Not yet.
might be?
I'd like to do that, but we have not yet. In fact, the model, I'll just show you here. Just close your eyes while I go through my, I included, I took this out because I didn't want to run over time. So these are just look at the upper right. So those are the plumes of the forecast from each member of the coupled model, initialized predictions. So you see those 20 kind of gray-blue lines. So they're all very consistent for the DJF this past winter of El Nino. But if we move over to, they are predicting a La Nina this winter, but there's quite a large spread across the forecast, at least the forecast done on the 1st of November. So yeah, I would actually like to run the same set once we reach kind of this coming autumn, and then I would expect, probably won't turn out this way. There's always surprises, but maybe the impacts from La Nina will actually be exacerbated by the background climate trends. Yep.
Okay, thank you. Yeah, thanks again, Clara.
Thank you.
Can I ask you to stick a little bit after? I want to go through the preparation for the lab, but if some people have a few more questions, Clara will stick a little bit longer. Yeah, then let me come back. I'm fixing something quickly. Oops. Oh. Ah. The slide disappear. Okay. I cannot go up to the first slide. I want to go up when I touch it. Up. Okay, thank you. Thank you so much. Yeah, then this is the check-in. Every day we will have a check-in to see what went well in the lab and what didn't go well. And I have a few clarifications that I want to give you to put you back on track. And don't worry, it happens every year. We have like problem with the account, and it was the first time we tried this tutorial queue because there were a lot of problem on Cheyenne derecho lately. Then this kind of issue is expected. Then don't be desperate yet. Then basically, this is the CSM tutorial webpage where you can find information about the agenda and the lab material. I hope everybody now have found this webpage. Then my first question, it looks like this. Then the first thing that I want really to make it clear, we have a rough guideline. On the first day, you are going to cover the basic. On the second day, you cover the simple XML modifications. Third day, you do name list troubleshooting, source mods, day 4, challenge exercise, and day 5, diagnostics. But this is like guidance. You have people in this room that have been running CSM for a long time, and you have people in this room that barely know a Unix command. Then we are coming from all background, and there is no right and wrong. I will stick with the people who go the slowest, because the other, they can manage on their own. Then this is a self-paced lab. If you are on day 3, if you are still on the first day of exercise, don't worry, it's okay. It's because you come with a different background. Then go at your own pace. This is what we give you. Then sometimes we have put a lot of more exercise. You don't have to go through every single exercise. We have more exercise because you have a few people who are more advanced and they go through more exercise. Then you don't have to do all of them, but you can ask us for some guidance if you need. Okay, then the first question, was everybody able to log on the ratio this morning? If not, I need to know, because everybody could log on the ratio and complete the prerequisite for success exercise that's inside here. I'm not touching the screen, but you have to do SSH, basically username, and everybody was able to go there. Okay, this is already good. Sometimes it doesn't happen yet. Then were you able to do, sorry, I did this quickly during lunch, and I see there's some typo. Tutorial. Were you able to do the tutorial one-time setup? Then I apologize. This morning, they were one place, and I swear I spent hours and hours to try to look at every link, but there was still an old link that was pointing to lab material, and it's why you were arriving on a location where this doesn't exist. It should have been fixed, but we didn't want you to go on this link. You were supposed to go, was expecting you to go on the tutorial one-time setup that's there, and this is the right information. Then if you have copied some of the stuff, there was another problem in this profile file that we fix after. If you have issue, you might have to recopy over the profile file, but it's a one-time setup. I swear, this time only one time. Then this is yeah, if you haven't been able to complete this, talk to us. It's a priority. Next thing, if you are a full-time participant, you have access to an account number. It's something that we are charged when you do your run. It's an account number UESM 0013. Then you will have access. The auditor will not have access to this. Sorry, I don't know why the screen is too small. And then we have also, for the full-time participant, a special reservation queue. What this is about is that when you submit a job, when you submit a run on derecho, it will go on a queue, but you are competing with everybody on the planet and that is using derecho. And sometimes the machine can be really, really busy. But you have 2 hours to do your stuff. Then we have this special tutorial queue. Then the instruction are to use this special tutorial queue and also the account. It's there. It's a tutorial queue and account. You should have the slide online also. And this is what you have. How do you use this? There are instructions on the web page, but I just recreate this small instruction. In theory, to use the project number, we have set this in your profile, and it should be fine. But now, how do you use the reservation queue? And it's only active during the lab. At 5:30, this queue, it goes away. Then if you have submitted a job and it didn't complete by 5:30, your job will die. Then if your job dies in the morning, then it can be just that we have this, because we are reserving a part of the machine just for you to do your simulation, but at 5:30 you will be gone. I asked, it was at 5 you stopped doing the lab. I asked 5:30, but we want to release all the node to the rest of the user because we don't want to sit on them if you are doing nothing. Then it's really, during the lab, you use this instruction. Outside the lab, you use this instruction. It's also on the website, but I put it here. Then basically you create your case, you do a setup, and then to use the tutorial queue, when you compile, you have to add this -q tutorial. And this morning it was not working, but CESL was able to hack PBS. I don't know how they do this, but they were supposed to make it there. Now it seems that it's working. If we are still issue, we will fix it. If you are outside of the lab, you just do this. You don't include any queue. Then also when you run the job, you have to do this XML change jobs queue equal tutorial and --false. It's because the queue are defined in CSM, the queue that exists on derecho, but this is one that was just created for this effort, then it doesn't exist through CSM. If you submit a job during the lab and after it doesn't complete, if you want to change the queue, you have to go on another queue that's called CPU. It's the regular queue. The auditor will have to use this one. But this is basically the 2 stuff here in green that you have to add. When you go in the solution of the exercise, you will not have this every time. You have to add it yourself. The reason is that we want this documentation to be available for people who are learning CSM, and we don't want to confuse them by putting this command that is just for you during this lab. Then it's why you have to go on this page that say tutorial queue and account, okay? If you don't do this, it will work anyway, but then you will be on competition with all the rest of the user. Then your job might not go through. And then tomorrow we will have a longer job, and this longer job, you absolutely don't want to submit it in the tutorial queue because it will be too long, it will die, and also when it will be running before dying, you will use the whole machine and nobody else in the room will be able to do anything. Then it's really important, but I will tell you this again tomorrow several times. Then there were another thing that was, yeah, I don't know why this song is completely all over, but okay. There is this, yeah, there were some people that were confused in the first exercise. It's because you have, in the CSM workflow, they will show you a generic example. When they say create new case, minus case, blah, 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 case, but it's not defined. It's like a name, a placeholder. Minus resolution res, it's not a resolution, it's just placeholder. And then after, under the comment, there were small note, no, don't enter the example above. At the comment line, you will create your first case in the exercise at the end of this section. I found this really confusing. I agree with people that got confused, but it was created this way. But then they want you to go, this is general documentation, and they want you to go in the exercise overview. And if you compare to the comment here now, it says the name of a case, and it says also resolution, that's a real number. Then this is, don't be confused. If at some point you type here and you say, I don't recognize this COMSET called COMSET. Yeah, of course, it's not a COMSET. The COMSET is B1850. Then it's, yeah, then this is, it was confusing. And I apologize that it was confusing, but it's because there were this small note. We were checking you know to read, and you're reading. No, I'm kidding. But it's, yeah, a lot of people do this. I think we should change this next year, but you will have to live with this for this year. Do you have any question? And then call us if you have problem. This is the first day we are doing this first exercise. Then call us if you have problem. You saw there were a lot of help in the room. In the morning, it was a little bit panicky because account was not set. The queue was not working. There were like a link in the documentation that was not working. I was having a panic attack, but every year it's the same. Then this is basically everything that should work. I love to say this. Then this is it. Then if you have question, yeah, each time I say to my son, I put your slide again.
That's very good.
Yeah, yeah. Okay, I'm going to record you to say it's very good. And, yeah.
I took a picture to send my son.
Yeah, they should do this together. Okay, then we are going to move to the library. There are snacks in the diamond room. If you don't know where's the diamond room, ask us when you are there. There is a secret entrance to move between the library and the diamond room. And then the people who want to talk with Clara, 1 minute. People who want to talk with Clara, she's still there. Okay? Thank you.
Exactly, that's where I was totally confused after having issues with my login.
Yeah.
big similarity in the spelling of D. Every time I type TEH and I saw you did that in the
Yeah,
grid.
yeah, yeah, yeah.
And I said,
Yeah,
okay,
yeah.
someone else
Yeah,
has
yeah,
that.
yeah, yeah.
All my Ds are my friends and students. And
Yeah.
But you cannot write D on the phone.
Yeah, 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 yeah.
TEH.
Yeah, 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 yeah. That is
Not
just
to
like, yeah, yeah.
point out, but
Yeah, 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 I know.
I'm
Yeah,
happy
yeah,
to
yeah.
see someone else.
Yeah, yeah, yeah. Yeah.
Please don't
The
mind.
finger, yeah, no, I don't mind at all. Yeah, yeah. Oops, sorry. Hey. Okay, then